KFUPM's commitment to solving global challenges through innovation, collaboration, and excellence. I am convinced that global challenges can only be overcome by joining forces. We believe in and advocate for partnership with other institutions to promote joint research and to create long-term values for society and for the environment. It's an exceptional opportunity to exchange ideas, share knowledge, and envision a more sustainable and innovative future. Last but not least, we eagerly look forward to an inspiring symposium, rich with insightful discussion and invaluable connection. Together, let's shape the transforming future of quantum computing and technology for both our kingdom and the international landscape. I'd like also to thank all the speakers and participants and wish all of you fruitful and vibrant discussion ahead at the Symposium on Quantum Computing and Technology. Again, I'd like to thank all the attendees here and all those who worked hard really to make this symposium a reality, from all the KFUPM committees, housing, security, KICS, which is KFUPM Institute for Knowledge Exchange, Dr. Filimban and his center. They really took a great effort in making this event happen. The College of Computing and Mathematics, represented by the Dean, he has also worked hand in hand with all of us to make this happen. So I hope all the best, and we look forward for a fruitful symposium. Thank you. Assalamu alaikum wa rahmatullahi.
Stand up a little bit closer to each other so we can take a group photo. After which we will have a break till 9:30.
بس بعلمك حاجة هنا. تعال. إذا جيت تقدر ترفع.
بسم الله. without further ado, let's start with the first speaker for today, Professor Arfan Siddiqui from UC Berkeley, presenting Computing with Imperfect Hardware.
Assalamu alaikum wa rahmatullah. Bismillah ar-Rahman ar-Rahim. Let me start also by adding my words of gratitude to all the organizers that have put this together. It is really a tremendous pleasure to be here, Professor Philip Ban, Professor Rao, others, so on and so forth, that have supported all the ongoing quantum activities here. And it's truly been a pleasure to work with KFUPM, its graduates, many of whom are sitting here, and to see the growth going forward. And we hope that this continues, inshallah. This morning's presentation is one where I wanted to intersect a number of different themes. It was said that we are in now the 100th year of quantum as declared by the UN. So my good friend and mentor here will ask, then where is the quantum computer? We're already 100 years into this endeavor. So I think the answer to that question is really reflected in my title, which is how does one compute with imperfect quantum hardware? And in particular, in 94, there was a tremendous transformation in this field when Peter Shor showed us how you can factor certain types of numbers with an algorithm that has quantum elements in it. And that's a really practical problem. The challenge, of course, it requires many qubits and many good qubits. And we are still trying to aspire to that challenge. So the natural question that comes up is, well, what can you do with hardware that you find natively in nature? And perhaps different problems are inspired by that, where another esteemed colleague will tell us the route to advantage in the afternoon. So I look forward to your route so that we can try to follow it, Professor Keys. Advance. Let me go to full screen mode, maybe. There we go. So these are the folks in my group at the moment that do all the hard work. I just give talks, so it'd be appropriate to start with showing them. And I wanted to start with this image because computing depends on hardware. After all, we start with a particular set of hardware and use it to encode and process numbers. And the Chinese, for example, have done that for millennia in this particular hardware, which is the abacus. And what's interesting in the abacus is that there are individual particles which you slide up and down, but they're not correlated with each other. Moving one particular bead doesn't change the bead next to it. And quantum mechanically, that's not how nature at its most fundamental level is wired up. We believe nature to be wired up, at least at scales where quantum mechanics is prominent, in a way that's entangled. This is this famous E word, entanglement. So an operational definition of entanglement for today is if you take two elements that are here, for example, right, a little bit hard to point, but let's say you take these two atoms. If you are able to describe them as the atom on the left and the atom on the right, then they're not entangled. Right? A description which requires both of them to be discussed is entanglement. Okay? So there is this fundamental connection that's there in nature, but why don't we feel it on a daily basis? That's because typically matter is entangled with many other things. And those other things don't talk to us. So the name of the game is to refine entanglement so that you may control it. That's really the premise of quantum computing. So what is really the power of quantum hardware? If you look at the transformation shown on the left, this is really what has happened, if you like, at the 30,000-foot view with classical computing. We have shrunk the size of the bit of the abacus. And you see, for your convenience, I put it in nanometers. Okay? So the beads on the left are fairly large, coming in at a very large number of nanometers. And we can shrink them down to about 10 nanometers. Okay? But the logic is fundamentally 0 or 1. That has not changed in that particular architecture. If we now go beyond, let's say, to the limit of 1 nanometer, and we start to look at individual atoms, then the rules of the game are changing. Then this quantum entanglement is possible. And in fact, it doesn't have to be atoms, which we'll talk about in just a second. It can be anything where quantum mechanics is observed. So in my own field, which we will talk about shortly, of superconducting circuits, that's a bit bigger, 100 nanometers. But what's fundamentally different is, first of all, your bits are rather analog. They're no longer 0 and 1 in the digital sense. They're any combination of 0 and 1. But more profoundly, they can be entangled together. So if you look on the screen, you'll see these light green lines between those bits, kind of illustrating how the atoms were connected. And when you connect them in that way, then the counting problem, I think, is very easily illustrated here. If you have a classical computer, you will increase capacity by adding 2. In the quantum computer, you will multiply by 2. So if you go down to 300, that's a very large number, and I think you really appreciate that when you write it out. Okay? So 2 to the power 300, and you will see these claims in the literature many times, that's about 20,000 times the number of particles in the visible or known universe. So if you were able to make very good bits that hold this entanglement, then you need only 300 of them. But it's very challenging to do this, and we will talk about that. It also opens up the door for resetting technology. Conventional computers use silicon MOSFETs or other devices, and there has been tremendous development in that material system. With quantum, we can start again and think about what's the right system. And there are many candidates, and we'll hear about that in this symposium. We can talk about individual elements in silicon or diamond defects, photonic circuits, trapped ion circuits, neutral atom circuits, and the like. And we saw in the headlines in the New York Times an experiment labeled quantum supremacy, where in fact a quantum machine could do something a classical machine could not. This is a tremendous proof of the theory. But as Professor Keyes will tell us, it has to do something useful. And that's, of course, something that we are working on. So let me then again give you one of those summary statements for quantum entanglement. Observing quantum entanglement took us about 100 years, plus or minus a decade. So we were able to do scientific experiments that showed, and that continue to show, that entanglement is our best understanding of the physical world. Building a quantum computer is a challenge of putting wires on entanglement. So wiring entanglement can be done in 2 ways. You can start with an atomic system, which naturally doesn't like to talk to its environment. So you have to add wires. Okay? But these wires should be very good. They should not spoil the entanglement. They should scale in an efficient fashion. And that's a disruptive technology of the one you were looking for, right? How to add those wires. The other route is to start with electronic circuits, and they already come with too many wires. We have to remove wires. So when we remove these channels to the outside world, then again you can access a quantum regime. So you see, when the question is asked which approach is perhaps the most powerful one, there is no clear answer. They're equally difficult in quantum mechanics and have very complementary challenges. In particular, if you have an electronic circuit, then the things that act as unwanted wires are materials defects, are radiation coming in from outer space. All of these channels of communication will break that entanglement. And that's really the challenge. One photon is too many in the circuit. One unpaired electron is too many in the circuit. Moreover, to control all of these technologies, we have to rethink about the entire stack. So there's a picture of something that I can hold 256 quantum bits from my lab, one of the dilution refrigerators that we have. And you see we start off with the quantum processing unit at the bottom, and then we move up to the package, the wiring, the backplane, the control electronics. All of those things have to be rethought about. So if you're thinking about disruptive technologies, it's important to realize that with 300 bits, you want to hold the energy capacity, the information capacity of the universe. Then what are the wires that are going to measure those 300 bits? And that's not an easy task, but one that's, of course, tremendously rich and the focus of many research endeavors. So the plan for today, in the brief half an hour that we have, I wanted to touch upon 4 topics, just giving you, again, the 10,000-foot view of some contemporary questions that are there, and then leave, of course, time for discussion at the end and later in the day. But I'm going to pause here and ask the audience, if there's something you wanted to learn about quantum computing, ask me now, so then in the next 30 minutes I can endeavor to answer it. Feel free to ask. Al-Bara Shafi, do you have a question? Yes, he's asking how do you deal with noise. We will talk about this. I wanted to break the ice. Thank you for participating in that ice-breaking exercise. Any other thoughts or questions? Yes. We will talk about this. Senior administrators may not be allowed to ask questions, but since we are friends, I will allow this, please. No, please, please, please. That is a fantastic question. So in fact, what is the data structure that to keep in this information in a rigid fashion? I have absolutely no clue. So in fact, on my last slide, I'm going to talk exactly about this. Yeah.
The question now, after all this progress, quantum technology, how far we are from reaching calculus 10 years, 20 years?
We are both near and far. We will reach something in 10 years. Whether or not what you want, we will, in the next 30 minutes, we'll endeavor to talk about this. I saw another hand here, at least one or two more. Okay, so we'll move forward, but what I want to say is feel free to stop me as we go forward. So first, let's talk a little bit about a superconducting processor, which is markedly different than a classical computer. The first point is, what is the bit? In a classical system, a bit for me is typically just a switch. Right, as illustrated here with a switch that really goes from 0 and 1 and a battery. Okay. To complete the circuit, you have to measure the voltage. So typically you put a resistor and measure the voltage across that circuit. The problem is that once you have a resistor or any elements which are dissipative, like a resistor, then the coherence that you're talking about is eaten up by that resistor. Because a resistor, in fact, will get entangled with your bit and carry the information with it in an uncontrolled fashion. So for superconducting circuits, we deviate from this model, at least for the ones that I'm going to talk about. So we look at something that's different than resistive, but again, rather fundamental. This is a piece of pottery that you put in an oven and it glows red. This is one of the reasons why quantum mechanics was invented, was really to explain this problem. We could not understand what is the light emission from solids, or black body radiation. So if you look at the body of this, these atoms are vibrating, and they are oscillators. And the amount of energy that they exchange with the environment is quantized, 1 photon at a time. So it's that quantum degree of freedom, that oscillator degree of freedom, that we're going to use in superconducting qubits. So you see that's profoundly different than using a resistor. It also means that the circuits to measure it will also be profoundly different. Okay. So we look at this oscillator and apply pulses to change its state, just like you would apply light to excite the atom. And you want to measure the light which is emitted. And for us, in the superconducting domain, that light is in the microwave frequency, not in the optical frequency. So this makes the challenge a bit hard. Okay. So you see, this one I put in blue, because now we're removing friction. We're removing this source of dissipation. The oscillator, the better you make your oscillator, the more coherent it is. Okay, so that is really the proxy, if you like. You want to make a very high Q oscillator. Okay. So what's the simplest oscillator that we typically make in superconducting qubits? This is called the transbund qubit. Let me see by a show of hands, how many of you have seen this word transbund qubit somewhere? Okay, very good. So this transbund qubit is just an LC circuit for the engineers. The L shown here, right, is a Josephson tunnel junction. Okay. So the idea is that a tunnel junction, you have two pieces of superconducting metal, and one by one, the Cooper pairs will tunnel across. Depending on how many pairs you have, that will be affecting the tunnel current. If you have few pairs, then there will be a small lag. If you have a lot, it will be a different lag, and that's called the kinetic inductance. Not a geometric one, but a kinetic one. So you end up having an inductor which is nonlinear. So this nonlinear inductor plus a capacitor gives you a nonlinear oscillator. Tamam, that's the end of the story. That's basically a transbund qubit. All other qubits allow you to put different controls, electrical control, magnetic field control, so on and so forth. But they are still based on this idea that in a classical harmonic oscillator, standard harmonic oscillator, all energies are allowed. In a quantum harmonic oscillator, only certain energies are allowed. They are separated by the same distance, as we learn in photonics, h bar omega. This anharmonic oscillator has 5% anharmonicity. So 0, 1, and 1, 2 differ by 5% in a transmon qubit. So that's how you can address only 2 levels and not the rest of them. And again, the frequency of oscillation here is somewhere between 1 and 10 gigahertz. So it's a 10 gigahertz atom, not a visible light object. Okay, so here's my qubit, and I'm hoping the slide will illustrate the following problem. How do I measure it? Right? Where do I put the wires? Right? After that long spiel about how wires can destroy your system, it's very important to think about how do you put wires on this. One of the typical things we do is to put it in a cavity, just like you would put an atom in a Fabry-Perot resonator. And if you put it in a cavity, that's the equation that goes with this. If you do not like the equations, just make them gloss over. If you are a mathematician, fall in love with them because they're important. But I put them there either way. So this particular equation is the Jaynes-Cumming Hamiltonian, which tells you how to swap an excitation from the atom, in this case the circuit, to the photon field. Okay, so this is a well-understood problem, studied by Jaynes in the 50s. Okay. You then think about a limit where the frequency of the oscillator is different than the frequency of the cavity. Okay. In which case, if you probe the transmission through this cavity, you will get 2 different frequencies. This is the fundamental way we read out qubits. If you're an electrical engineer and you put a dielectric material in a capacitor, that's exactly what you're doing, but this dielectric is a single atom. So depending on whether it points dipole up or down, it will change the response. But it's the same physics. Okay. Now here's the tricky part. All the action happens when there's about 1 photon in the resonator, 1 microwave photon. If you put too many, then this physics doesn't work. It starts to break down. So to measure 1 microwave photon, there is no device, at least until very recently, that you can buy commercially. So we spent many years trying to measure 1 microwave photon. Okay. The width of these curves is given by the noise. If you use commercial electronics, those widths will be too big, and you cannot separate out the 2 states. So that's the fundamental problem. You can separate them more by adding more photons, but then quantum mechanics doesn't work. If it gets too wide, then classical mechanics will kill you. Okay. So we thought for many years how to make an amplifier. And this is one of my favorite images. I don't know, I may have used this at least 5 years ago, because I will never lose this image, I think. So the idea of an amplifier is that somehow you must bias a system so that it wants to change very rapidly, but in a very controlled fashion. And this for me is the camel with too much straw on its back. So one more piece of straw will go ahead and cause the camel to sit down. Over many years, the community, we have turned that now into an equation. Right? So this gamma m means the rate at which information is coming from the camel, and this gamma phi is the dephasing. How much noise do you put in from quantum mechanics? And the theory fundamentally lower bounds it. Right? There's a minimum amount of dephasing you must have. So how do you hit this bound? Because that's critical for measuring a quantum system. So pieces that go into this are about what is the correlation between the thing that you are measuring and your measurement apparatus. That will be difficult to see with that equation, but let me illustrate it in the following way. If you want to measure something which is round, your detector should be round. Because if you measure with something which is square, you are wasting information. Right? So you calculate the quantum states like in the logo of your conference. You have that ket. You have to look at the overlap between the thing you're measuring and your measurement apparatus. And that's how one makes a quantum limited amplifier. It took us many years in the community to appreciate that. Here's, I think, generation number 17 of those types of devices that we make in the lab. And then we start to put them together. And you ask the question, Khalil Harabi, we've made now progress with all the qubits. How far are we? Well, we start to put them together in a chip. We no longer call them qubits. We call them QPUs to illustrate that we're actually building something that can compute. But we have folks, colleagues from IBM, and I look forward to their presentations. And I wanted to quote an ex-IBM person, Rolf Landauer. One of Rolf Landauer's first quotes was, "Information is physical." I illustrated that with the abacus. The second quote, which was written in his obituary by Seth Lloyd in Nature, is this one, where he says, "This proposal, like all proposals for quantum computation, relies on speculative technology, does not in its current form take into account all possible sources of noise, unreliability, and manufacturing error, and probably will not work." That's a very forward-looking quote. Right? So in fact, what we're going to talk about is how do we make progress on all of these things to find something that does work. And maybe I think the point I want to make is it will work in a way that we didn't expect. Okay. Let's talk about the surface. If you take this particular chip, which has niobium metal on it, and do very high resolution transmission electron microscopy of the surface, you will see what are those defects. You're asked about coherence. Yeah. This was done by the National Center of Electron Microscopy at LBL. Okay. And you can see the scale bar, that's a 5 nanometer scale bar on the top. And you can start to see niobium in its different oxides, NBO, NBO2, NB2O5. You can see epitaxial planes with the silicon. That 3 or 4 nanometers on top is killing your coherence. Right? So to engineer that out is a major challenge. And we made progress with that. But that's the short answer. Surfaces and interfaces. And I know our next speaker is going to talk about this. So I thought I'd put in this slide. Okay. What do these amorphous materials do? They represent systems which look like qubits, so-called two-level systems or defects. Here's an experiment where people change the strain to map out the spectrum of these two-level systems, and you see how many there are. How dense are the defects on a chip? So that's really the challenge of material science, to get rid of all of those defects. Okay. What about the junction itself? This is now an image, a TEM image, showing you the composition as we go across the tunnel barrier. If you look on the left, that little piece of oxide, this is superconductor, that's the junction. And you can see the oxygen varies by 20, 30%, even across the junction. So another material science challenge. Also very challenging to get that data, but nonetheless very revealing. So that's the materials piece. And the question is it a bottomless pit? You keep improving materials. When do I stop improving materials? The other challenge is, well, maybe I can make a better circuit than the transmon. Maybe I make a circuit which is more resilient to noise. And so where does the slider sit? I don't know if anyone remembers, this is a very famous Muppet. This is Beaker, the Muppet. He's an experimentalist. So you see, Beaker is always given the most challenging of tasks: go measure a qubit. Okay. So if Beaker is measuring a transmon qubit, you see there's a lot of noise channels in the environment: phonons, photons, defects, so on and so forth. And all of them couple about as strongly as Beaker. So it's very hard to get that information out of the hands of those other channels. But if I can make a different circuit, maybe one that works on magnetic flux rather than charge, now I add more junctions, but I remove some channels. And I can go more and more, where I start to build in topology into the circuit, where certain modes are then forbidden, right? Even more. So the challenge, of course, is if you hide your circuit too well, you will not be able to find it either. And this is the challenge of a Majorana qubit. So somewhere the engineer needs to find happiness of how much to hide it and how much to improve materials. So we have started to build circuits that are well beyond the transmon, and they require elements like this. This is an array of 100 or 500 suspended Josephson junctions in air. And when you remove the substrate, you get a very pure inductor. Okay. And we can make now resonators out of this. We can make qubits out of this. You can see the qubit junction is here. The rest of it is folded up for the inductor. Okay. It's a beautiful spectrum, no defects. So there are ways where we can start to remove coupling to these unwanted modes in a very clean way. So that was the first topic, right, where I showed you a little bit between the trade-off between materials and architecture. It's an open question. We don't know where to move that slider, but one to think about. Then we want to execute an algorithm. Okay, this is a very old graph, and I know you will update us in the afternoon, but I wanted to start from this graph from the Boston Consulting Group. On the vertical axis is robustness to noise and errors. So if you're highly robust to errors, you can have noisy qubits, imperfect qubits, so on and so forth. If you have low resistance, then you need very good qubits. and probably error correction to do this. And on the horizontal axis is the question you asked. How much better is it? Is it polynomially better, or is it exponentially better? In the beginning, I told you about this exponential speed up. Oops. Polynomially better. So you see, sure algorithm here on the lower right, exponential speed up, but it requires lots of really good qubits. And there are a few other problems like that. But then we have a lot of different algorithms that have come up. Some have a mixture of quantum and classical, and it's a little bit under debate as how much better will these actually do than a classical algorithm. Okay? And I want to actually add another axis to this graph. Maybe all of these are wrong, right? In your spirit of disruptive ideas. For the following reason. As an experimentalist, I have hardware. If I want to get grant funding from CACT or someplace else, I figure out what that hardware does. We are imposing the problem. Right? We would like to solve the ground state of a Hamiltonian. We want to diagonalize a matrix. That's great for classical computers, maybe not so hot for quantum ones. So what's the natural problem that quantum computers, in my point of view, want to solve? They solve for dynamics. They show you how to propagate a very complex system in time. Right? Will I be happy tomorrow? There's a lot of factors in that. So if you want to entangle that all together, you can have that wave function advance in time. So in chemistry, for example, we can think about chemical dynamics, not just ground states. So a different set of problems. Moreover, how much entanglement do you really need? If you look at any one of these algorithms, which step requires the entanglement and how much? It's not obvious. It's a tricky question. So if this resource is so precious, this quantum entanglement, one should know when you need it and how good it should be and how often you need it. So just some thoughts about algorithm development, because you asked, how can we think about from the classical world, algorithms? You can think about even in the quantum world. Okay. To your question, how far are we from this? This graph is great because I draw it in log scale. I never have to change it. Every 5 years, I move like 1 millimeter on this graph. The horizontal axis tells you how good is your qubit, whether it's a gate or what have you. The vertical axis asks, how many qubits do you have? So you see the current state of the art is something like 0.1% error and a few hundred or 1,000 qubits. That's that dashed line here, right? On the lower left here. This is the limit of what a classical machine can do, but we start to get closer, right? And as you go to this particular avoided crossing here, we would like to make it a real crossing, where you have some improvements in the algorithm, some improvements in your materials, and perhaps you will cross that boundary. That's there. The real target, of course, is something which is fault tolerant. So the idea there is that somehow the error rate of your qubits needs to get better as you add more qubits by running error correction. And that's a real challenging problem. But that's really the prize at the end of the day. Okay. So what about chemistry? When you try to simulate the structure of a chemical molecule, you can basically have two problems. Typically, you run out of memory in your computer. Any supercomputer, take the one shown here, you run out of memory because the number of configurations is 2 to the n, or however many atoms you have. Okay. Then, of course, there are many approximate methods in chemistry. But what you can do is something called a variational algorithm or a hybrid algorithm, perhaps of the one that you were intimating in the morning. And the idea is find the one hard step and do that using quantum mechanics. So in this particular case, it's the ground state of some very complicated molecule. So you just have them interact and read out the answer. Right? They will have basically a hardware solver for this problem. And we have done this. Many others, of course, have done this. This is a spectrum of hydrogen with its excited states that we pulled out of our quantum machine that we built. It does a good job. You get into chemical accuracy. But it's very difficult to scale. The number of measurements you need is not so easy. Error rate is tricky, so on and so forth. So one of the things you can try to do then is I asked yet another orthogonal question. Do we really need to calculate all the energy of the ground states? Maybe not, right? So here's my very, very naive thought on this. If you look at pharmaceutical drug development, what is currently being done, and perhaps what could be done with the quantum computer? Right now, it's estimated that it takes $2.5 billion to make one new drug. And it's interesting that the preclinical research selects only 0.1% of small molecules for critical trial. That's a lot of molecules. You have to go through and find a very small fraction. And then 10% of the clinical trials are successful. So you lose another 0.1 on top of that. Okay. So I asked some folks that are in this industry, what's the slow step? Why are we having such a low success rate in probability? And the answer is, it's very hard to understand the quantum mechanics of small molecules. Is it going to confer to the right, to the left, bind to this or not? So I put forward that maybe you just don't want to find the ground state. You just want to find the correlator that improves that 10% accuracy to 20%, in which case you knocked off $1.25 billion for each drug. Okay? That's a much more reasonable problem to think about for understanding where quantum mechanics may guide your intuition rather than saying, let's find complete information. What can we do with noise? Are we truly limited by noise? Can we do things that are more powerful? How many of you are familiar with this kind of diagram? Let me see by show of hands. All right, very good. So what's happening here is on each one of these lines is a qubit, right? That's there, and the horizontal line tells you the gate operations that you do on these qubits. And what you're limited by typically is the gate depth, right? We can't run too many operations. So at some point, information is lost in the system. And if we can prevent that information loss, we can run a deeper circuit. So it begs us to ask, well, where is this information loss? How can we parameterize that? So again, getting a little bit mathematical, but the general idea is quantum mechanics, or state of a qubit, is a vector. It points someplace. So you can have two types of errors. I want to make it move by 90 degrees, and I do 91 degrees. That's an error. I didn't shrink the size of the vector, it's just in the wrong spot. So you see the information is not lost, it's just in a different spot. I need to look 1 degree more. If I have decoherence, then it's truly lost to the environment. So the length of the vector shrinks, it becomes a mixed state that's there. So if you look in a matrix representation, when it shrinks, those are diagonal elements. When it's rotated, those are off-diagonal elements. And as you run these gate operations, that's multiplying by this matrix again and again and again, and the errors along the diagonal accumulate very differently than errors along the off-diagonal. And it's the off-diagonal errors that will actually kill you much faster, right? Which is strange. You would have thought it's the decoherence that will kill you, but no, it's actually the coherent error that kills you. So you see the diagonal is a cosine which scales to first order as 1, and the off-diagonal scales as x. Right? That's what's killing you. So we tried to measure, so this is, for example, a similar matrix for a certain number of qubits. If we only had error along these kind of depolarizing or randomizing channels, it would be along the diagonal. But you see we have colors everywhere. So that means we have a lot of the other type of off-diagonal error. So if you start to add random circuits, you see I can kill all the off-diagonal errors, right? Because that's a random process. So we spent a lot of time on this randomized compiling. So the idea would be is if I can add this randomization to an algorithm, I should be able to run a more complex one. And it's absolutely true. And you see, of course, many entities using this type of noise mitigation now. So the problem we looked at was scattering of 2 neutrons. Okay. That problem has a classical part and a quantum part. The quantum part is basically, if you like, from the Feynman diagram or the field theory of interacting particles. The position is the classical part. So you can do a variational calculation with this, right? And we did this. We encoded in qubits, right? And then, in fact, you can see that's the gate structure on the bottom. It has like 60 C0 gates. That's a lot, right? Can you run this 60 C0s with something which is noisy? If you look in the upper left, the dots are what you get out of our quantum machine. The lines are the exact simulation. And if you don't do any of this noise mitigation, there's quite a discrepancy between those dots and lines. However, as you add more of these techniques, you get the lower right. And you can see with the same hardware and same noise, I can do a lot better. So just starting to understand how to maximize what's coming out of your quantum machine. So finally, to end up, I want to spend 5 minutes, again, asking a question which tries to, again, break the mold. Why use only 2 states? Right? Why don't we use 3 or 4 or more? And you can, and this is becoming now very popular in the field. So I'm going to just flash through some of these slides to whet your appetite so that we can go to questions. So, by the way, the British knew about this a long time ago. So the treasurer of the Poor Law Union in Great Torrington, England, Thomas Fowler, was tasked with calculating what each parish owed in a tax. And they used this pre-decimal system. All values had to be calculated in farthings, which are 1/960th of a pound, 1/48th of a shilling, and 1/4 of a penny. That's not fun to do. But he figured out how to use ternary logic to do this, and it was written up in the minutes of the British Society for Advancement of Science in 1840. Mr. Fowler's machine that uses ternary logic for doing this. And that's even a replica of this machine. So even before digital computers that were binary, there were other ideas of computing. And the Soviets actually made a lot of progress with this. 50 machines were built that actually use ternary logic. So how do you take a transmon from a qubit to a qudit? Well, you just use the rest of the levels. We typically have 4 or 5 of them. We have to re-engineer the circuit, but it's doable. And you can go ahead and read out the circuit in the lower right, so on and so forth. Okay, with high fidelity as shown over here, 99, 98% fidelity. Okay, I leave this math because I know that Ibrahim over there from Qasim is real mathematics aficionado. So if you use a different group, not the poly group that you learn in quantum mechanics for 2x2 matrices, the while group will let you do qubits. Okay, so there is good mathematics for doing this. How do you actually make a gate? If you have 2 qubits, they're coupled. If you excite one qubit at the frequency of the other one, the first qubit acts like a filter because you're off resonance, right? If you change the state of the qubit, you change this curve, right? And what happens then, of course, is you have an out-of-phase oscillation. And when you're 180 degrees out of phase, you get a C0 gate. Okay, so I wanted to leave you with that recipe for making a C0 gate. Take an oscillator off resonance, and you get a C0 gate. You can do this then for 3 levels or more levels. You just get more terms. Okay? You can go measure those terms, as we did, and you make gates out of them. Okay? And then you do randomized benchmarking for experts to figure out how good those gates are. It's a bit tricky because now you have 0, 1, and 2. So there are different decay channels, and you got to get the right mathematical set for doing that. And then you do 2 Q-trit gates, right, and benchmark the fidelity, and we're starting to get very high fidelity, 96, 99, and some of the other ones I'll show you. Okay. The critical piece is here. If you have 3 levels, is it better than having 2 levels? If you take any unitary operator that you want to write in this quantum algorithm, you can see I can express it very rapidly with 3 levels, any Haar random unitary. So I need less gates to express any circuit. So there's utility right there. Okay? That's the point of this graph. Finally, I toyed with this idea of how much entanglement do you need. You create this entanglement on demand. Maybe you make the qubit on demand. Maybe we don't need to have these qubits alive all the time. So you can start to think about systems which you drive in time to become qudits or qubits when you need them. So when you don't need them, they're just in the off state. So just think about having a pendulum where you rotate your head at the frequency of the pendulum, right? So that's a different world. It's the rotating frame. So we can make these so-called Floquet qubits, and they are solutions not of the Schrodinger equation, but of the Floquet equation, which looks like a block equation for those that work on materials. The utility of this is you can go ahead and change the frequencies on demand. You can get couplings on demand, which avoid many restrictions in quantum mechanics. Quantum mechanics will restrict certain level transitions because they violate parity. They violate angular momentum, so on and so forth, conservation. So this allows you to get around that. Okay? So in fact, what we can do is you have pairs of levels. If you want them to interact, you can actually go ahead and excite them with a photon, or you can bring them into resonance. These are 2 different interactions in quantum mechanics, right? A level that you climb versus a level you bring in resonance. So one is an XX, the other one XY interaction. So you are actually able to do both of these interactions, which really opens up the field for us. Okay? So the plan then is you apply a pulse, you go into this state where it's actually a qubit, and you turn it off, and you have to figure out how to do it adiabatically, so you don't excite other transitions, which we can do. And then what you can do is you can use this as a machine to generate entanglement. This is real data, not calculation. So here's a Bell state for 2 states, 3 states, 4 states. And you can see the quality of the Manhattan plot. There's almost nothing in the background. Right? The fidelity starts with 99%. very rapid generation, because now we don't need to go ahead and do these quantum mechanical restricted swaps. We can go much faster. And then you can even distribute it in an array of qubits. So for example, I can move this entanglement around to make something even bigger. Okay. In fact, I can make even Schrodinger cat states that are quite useful in metrology. So I can do that here by this mechanism. So just to show you, maybe we want to relax the model of having a qubit that's there all the time. Just generate the entanglement and the qubit when you need it. So final slide is this one, saying that as you get more levels, you can also get higher dimensional gates. Not just 2 Qudits, but 3 Qudits, 4 Qudits, Toffoli gates. All of those things are now accessible. So for example, here to my knowledge is the first example of a 4-qubit Toffoli gate that we've made with very good fidelity here. So anyway, I want to leave you with this slide before we go to questions. Perhaps to try to answer your question, how many more years? I still didn't put a timeline there. That gets us in trouble. If you look at the development of the classical integrated circuit, if you back down to the 40s, right, to what we have now, 80 years, you see there were many interesting developments. One of them was the development of the integrated circuit. And this allowed one for a low cost to generate these components, to change them, so on and so forth. The current state of the art in superconducting technologies is that you'll spend $100 million to build a machine that will be obsolete by the time you build the machine. Right? So that's a real barrier to entry in changing designs. Right? If you have to change the stack for every little thing that I mentioned, that's difficult. So to develop this quantum integrated circuit will be tremendously transformative, in my viewpoint. It also requires a horizontal ecosystem, where not everything is done under one roof, but we have partners, where people think about what about the wires, which was the question you asked, right? What about the algorithms? What about the data storage structures? These are all very hard problems and very worthy problems to look at. So with this horizontal ecosystem, I hope, this is where I left it blank, in some year 20 dash, we will be able to actually get an integrated circuit where this graph will be realized. So you see the promise of quantum computing comes when you don't need more classical wires to control it than the quantum degrees of freedom. If you need 2 to the n classical wires, it will never work. We're not there yet. We have to get to this crossover. So with that, I think we still have 5 minutes for questions. So I stop here and take your questions.
Thank you very much, Professor Arfan, for the very insightful presentation. I have 2 questions for you. The first one is, could you please share with us your thought about why you have decided to go with the superconducting qubit? Because in market or in research, there are different technologies, and most of your research, if it's not all, is in this area. My second question is about, can you please tell us more about the performance of the machines that you are working on in terms of number of qubits, fidelity? You have mentioned 99% fidelity, which is so interesting to learn. Thank you very much.
Okay, so the first question of why am I working with superconducting qubits, this was really easy to answer. So I started working with these circuits in '97, so no qubit was invented by that time. So I started working on detectors for terahertz frequencies. '99 was when the first qubit was fabricated. So the reason I work with these circuits is that's the only thing I know how to do. So it's really easy. Well, maybe know how to do. The other ones I can certainly tell you I don't know how to do. But also for me, it was spending many years on quantum measurement, collapse of the wave function, fundamental questions in quantum mechanics, which we've written up in a book recently. So this qubit technology for me is a way to test quantum mechanics. And to be honest, I have a pretty strong feeling, at least in my mind, that this theory will break down, right, at some point. We change our theories of physics every few hundred years due to new experiments. The quantum computer will certainly test quantum mechanics. So that's the first question. The second question was of fidelity numbers. So if you want to talk about raw 2-qubit fidelity, let's say of 2 levels, we can exceed 3 nines. So 999 on a cross-resonance gate that's there. If you look at fidelities of things that have higher dimensions, we are still, for example, I've had a slide in there we can go back to, but 98, 99. But remember, that enters in a much softer way because my Hilbert space is much bigger. right? So for example, if you have a Toffoli gate with like 95% fidelity, it's still better than all the other gates because you would actually have to create all those swaps to go do this. So one has to keep those numbers in mind. Does that roughly answer the fidelity numbers? Readout fidelity over 99, that's just a question of measurement time versus cavity decay.
Yeah, thank you, Professor Arfan, for this nice presentation. I have many questions, but I will be limited to one because my colleague wants to answer. Since now you opened the new channel, we are not going to use only 2 levels, we are going to use many levels. So my question is this new path or new way, is it going to reduce the number of qubits you be used for as a 2 level? So you can use, for example, 5, 10, and you reduce the number of qubits. If you can find such a way to couple levels or decouple them, will have a consequence of reducing the number of qubits required for quantum computing. And thank you.
أحسن بالضبط. So yes, exactly this. If you can fully entangle the space, it goes down. And that's why it took us a while, because people had many level system, but they didn't entangle the space. Right? So for example, when we're working with two levels of a transmon, you have those other levels, you're just not entangling them. But yes, we are able to fully entangle this, and it reduces it significantly, right? Because it goes as d to the n. So we are able to run many algorithms much faster. Moreover, the connectivity also makes it a lot easier. Because I think we will have a presentation from Quantum, ion traps have a different connectivity, so we can also artificially generate that connectivity when needed, which is useful for us.
Thank you, Dr. Arfan, for this wonderful talk. My question is about quantum and AI. So Google named their lab Quantum AI. So my question is, what's the relationship between quantum and AI and statistical learning? Is there a deep connect, or is just
I think I lost the last piece, but it was probably something. Okay. So I don't know about the precise naming of the Google lab, but I will talk a little bit about maybe intersections between quantum mechanics, quantum computing, and AI. So there is one level where you use machine learning to accelerate standard tasks in quantum information processing, but those are classical tasks, right? I have to figure out what the noise model is, I have to figure out how to tune up my qubit, so on and so forth. So you would be using AI as you would be using it in any other computational task. The other direction is an interesting one also. Is there something in quantum mechanics that can make usual machine learning go faster? And that's an interesting story that goes back and forth. So for example, many of the algorithms in learning that require a neural network or feed forward or so on and so forth, gradient descent, involve diagonalizing matrices. So you can try to think about using the HHL algorithm to do this. However, it comes with many strings attached. The matrices have to be sparse and so on and so forth. So it was in fact put forward as a problem by Scott Aronson to Edwin Tang, a student at that time, to prove some quantum algorithm is best in class. He ended up finding a classical one which is better than the quantum. So it's a bit tricky to figure out how to do this machine learning where it gets better by some quantum routine. I would feel naively with phase estimation it will certainly go better because it's like Shor's problem. It's the inverse of the Fourier transform. But again, that's a problem that's hard in the number of qubits.
I have a question about the length scale of the devices.
There you go.
The length scale of devices. What is the length of the bridges, the overhang bridges, and the roller coaster ribbons?
Okay, very good. So the junction itself is typically less than a micron. So if you take 500 of them, that's 500 microns that go across. And typically on this 500 micron sub-millimeter length, you can have enough tension in the bridge to hold it so it doesn't collapse. If you also notice that some of the bridges, they turn left and right, that's to balance the stress. If you had them just straight, they twist. So that's right. So that's a different one. So we actually peel it off on purpose to have it coil. That's there. So there are many MEMS techniques to control that stress, but the dimension is of order a millimeter or less.
Yeah. I have a question about the readout or change the state of the qubit. If you want to send a frequency that's equal to the qubit frequency or the resonator frequency, and how to distinguish between other qubits if you are using only transmon qubits.
Yes, this frequency crowding problem is there. So you excite at the resonator frequency, not at the qubit frequency, because they couple dispersively off resonance. But you will certainly have this problem of too many frequencies in a small band. And this problem gets very bad when you don't control the fabrication well enough, right? So there's 5% dispersion in your frequency that limits how many you can put in. So there are other ways around this. If you use, let's say, flux-based qubits, you can use a transition that is very far away. So for a fluxonium qubit, I can make a 2 gigahertz qubit and have a 10 gigahertz resonator, right? Because there is a matrix element that couples those things that are there, which doesn't exist in the transmon. So there are different ways to engineer readout schemes with quantum mechanical coupling when you have more than 2 levels. Okay.
Yes, I have 2 questions here.
Yes.
Yeah. Yeah. So the first question is about the noise you are talking about. So the noise, is it coming from the imperfection, or you are talking about the noise that is fundamental, that is in or what we call the short noise in open systems? So when you read, for example, the information, so it's an open system, you can consider your system as open. So is it that one? So it's the imperfection.
It's technical noise. And in particular, this kind of coherent error is crosstalk, right? And this crosstalk could be classical, right, where your wires just couple, but in fact, it can be quantum mechanical. So for example, you have a coupling that doesn't turn off, right? In a transistor, you turn it on and off by 9 orders of magnitude, but in quantum mechanics, that's why I showed you the J-Stubbings Hamiltonian. Even with 0 photons, there's coupling. So it's typically that crosstalk that kills you.
And my second question, if you allow me, the 2-level system, you're considering the 2 energies are as fixed. Is there any work where the statistics over these energies are done?
Yeah, so the 2-level system is basically this TLS acronym. I think a more appropriate acronym is SWN, Systems We Do Not Know. So we have absolutely no clue. What is this 2-level system? It could be dangling bonds, it could be quasi-particles, it could be all of them. So I think this is a great question, saying that we may not have one mechanism. The levels may change, and as we start to unravel this, we will learn a lot more about that.
Thank you. Super presentation. Thank you. I'm glad I came. I just want to make a comment on your presentation. I would say, in summary, the struggle is on, the future is unclear.
I will change it slightly. The future for me is very clear. Because you see...
That's the difference between a speaker and an audience.
No, you see, I would bet that the technology we will have will look nothing like this. Right? Because in the 50s, you asked how many transistors, the question we're asking is how many vacuum tubes can I make into an integrated circuit? None, right? So I asked actually someone that was working on the ENIAC, how many vacuum tubes did you have? They had 17,000. You guys at IBM will build 17,000 qubits, right? So we will pass that. So, but the point being is now you have access to a new handle on the world, which we didn't have before. That will be transformative. The same thing happened with the laser. What do we do with the laser in the 60s, aside from military applications? So the future is bright, but it won't look like that. So you're right.
There's another component, Doctor, is the cognition levels are high and also the tools and technologies available now. So the baseline is much better.
Yes, yes. Also, we demand a lot, right? We demand a lot. We write down the equation, tomorrow we want the result, right? So scientific endeavor will take a little bit of time, but we should be rigorous with our questions. Perhaps less demanding with the ROI, but rigorous with the questions.
I have a question right here.
There you are.
So what do you think about bosonic encoding? You know, cat code, I think you didn't mention anything about that, but you worked on some bosonic encoding. So cat codes, GKP codes.
Yes.
Is this promising? Or?
Yes. Yeah, I think it's fantastic, right? So I think the general subject, which is interesting to me, is noise bias. So the idea is if you try to correct for all errors, this is a very difficult proposition, right? You need many, many qubits. So you can build a noise bias that only certain noise channels exist and only correct for those. This may seem like an obvious thing, but it's actually not so trivial, because if you have an error in one channel, since they're entangled, it goes to the other channel. But it's not so easy to actually come up with logic, which is noise bias. So if you use a cat code that has bosonic encoding, or a GKP code on a lattice, right, that has different noise encodings, they are great, right? And we do that. But again, you're moving along this horizontal line. The challenge now is how do I do a protected gate?
So, yeah, can you comment on the difficulty? Like, stabilizing seems to be an easy problem.
Yep.
Make eigenstates and all that, but then making, you know, a grid of these What are your thoughts?
I can make a grid. I don't know how to do a gate. That's protected. If you figure that out, let me know. Instant job. But that's the challenge, right? I mean, you protect a qubit, but then how do you get them to interact without losing the protection? Not trivial.
Hello.
Yes.
I don't know if this falls under the systems we do not know
yes.
category, but speaking of Qudits or higher level gates, wouldn't that make them more susceptible to decoherence if you're reducing the number of Qudits and using extra levels?
Yes. So you're 100% correct. As you increase the number of channels, the number of wires, then you have that many more ways for the system to go wrong. But what may happen, and certainly is the case for the transmon system that we use, those channels are similar. So the same decoherence mechanism is affecting 1 and 2 as it is 3. So if I correct one of them, I kind of fixed all of them at the same time. Now, quantum mechanically, though, we have to be careful, because now your Hamiltonian has many more modes, and it can certainly have these pitfalls. So you're absolutely right. But hopefully, the idea is that we can engineer a little bit better than we can fabricate. So. Tamam? Okay. Thank you.
And now for our second speaker of the day, Dr. Salim Rao from KFUPM, presenting Sustained Enhancement in Quantum Circuits via Air Interface Treatment.
Assalamu alaikum. So thank you very much for the nice talk from Professor Irfan, and he built the platform for me. Okay, what I would like to discuss, the background, he already covered everything. So the topic of, the title of my talk is Enhancement in the Coherence. So I hope now all of you have good idea what is the major bottleneck in developing a quantum computer, and that is the noise. So I work in collaboration with Professor Irfan, okay, on improving the coherence time of the qubit. I am physically a material physicist and look at the coherence, improvement in the coherence, not from the design factor, okay, purely from the material point of view. So I will, based upon this Professor Irfan's talk, I can go over some of my initial slides very quickly because he built the base and I can use it. So outline of my talk will be superconducting quantum circuits. Professor Irfan already explained it. Okay, I will talk about in more detail the TLS losses. Okay, and Professor Irfan already mentioned it. This is the only theory we have to explain the decoherence. Okay, this is not only theory, this is the way we understand it. Okay, at the end he said there might be some other ways. Okay, we don't know why there is a loss. But as of today, this is the best understanding of the loss in a quantum circuits. And how we can reduce these losses, okay, and particularly, as I said, from the material point of view, oxide is one of the major hosts of these TLS losses. I will talk about it, how we can check it, and how we can get rid of it. So, different types of qubits. Dr. Fan already talked about it. So, but I will focus on this type of qubit, which is based on a nonlinear quantized LC circuit. Okay, so the major advantage of this superconducting qubit is you can see, okay, atom, of course, the best qubit, but how to manipulate it, how to control it, it's very difficult. Spin is also a very good qubit. Again, the problem is the control and having large number of qubits. Although there is a development in all other areas, okay, but one of the major areas is superconducting circuits. Major advantages, we have the fabrication technology. All of you have the mobile phone in your pocket, okay, with billions of circuits, okay, in a microprocessor. So fabrication is not a limit. Okay, if you ask, give me a processor with 1 million qubit, 1 billion qubit, you can fabricate it. But it's useless because of the decoherence. Circuit is too noisy, you cannot get any type of quantum processing inside those processors. So we use two types of LC circuits. One is readout. That is the cavity. Cavity is also a simple linear oscillator and non-linear oscillator. So we use the linear oscillator as a readout, as a control, and non-linear oscillator as a qubit. And you can transfer these two components onto the chip. Your resonator is just simply a metallic strip you can see in the middle. That is coplanar waveguide resonators. Engineers and physicists understand it very well, and we can have the LC circuit very close to it, so they are coupled to each other, and we can have a nice, interesting quantum mechanics over there, and we can use it for the quantum information processing. So chip is only at the bottom. So one of the most promising qubit, is the transmon qubit. As Professor Irfan mentioned it, I would like to highlight one thing. The transmon qubit, the charge noise is a big issue in a qubit. In a transmon qubit, you just control the charge noise. How you control it? By putting a big capacitor, in this circuit. So big capacitor is, think about it, if you have a C, you add a drop of water, and you take the drop of water, there is no change in energy level. That's a basically concept we have in the transmon qubit. We control the charge noise over there. That's a very tricky noise. You cannot control it. You are dealing with the circuit, and you're talking about the circuit is not losing or gaining an electron. But we can overcome this problem using this transmon qubit. This is one of the most popular qubit. We have some compromise on the non-linearity, but nowadays it's no more issue because we have very good microwave control from the electrical engineers. So now, another thing is, the fabrication is not an issue. The physics of these circuits is same as the physics of the cavity QEDs. The physicists are working on this cavity QEDs for decades. They understand the theory, they can do the experiment. So physics of the cavity QED is same as the physics of the circuit QEDs. So we don't have to put any extra effort to develop the theories. So whatever the physics of the cavity, same is the physics of the CPW resonators. Whatever the physics of the atom, same is the physics of the transmon qubit. So we can, there is a one-to-one relationship. Efforts of the physicists in a theory more than 70 years, and experimentalist knowledge for decades, we can transfer it to the circuit QEDs. So the question is, if everything is ready, as Dr. Professor Irfan mentioned, we can have this whole setup over there. We can design the things arithmetically. We can transfer into a circuit. We can generate it. We can control it, the classical computer. So everything is ready. So why don't we have a commercial scale quantum computers? The reason is the coherence. So now, so as I mentioned, we can have millions of qubits, theoretically possible, but we don't do it because they are too noisy. We don't have any useful information out of it. So basically, it's a lifetime of the qubit. But in a language of physics, we call it, say, coherence of the qubit. So lifetime of the qubit is an important issue. The qubit don't maintain its state. It changes with the time. And of course, when you're running an algorithm, the computer scientists believe in this thing. I prepared this state, the qubit is in this state, and you want to take it to the new state. But if the state is changed, and you go to the new state, it will be not that state what it was originally. So we need the high coherence in the quantum circuits. So low coherence, as Dr. Fahd mentioned, talk about it. There's two channels. One is the communication or connection to the external world. We want to minimize it. And second is the uncontrolled. That is, our qubit is going to talk about its environment, because there is a lot of two-level system. There is a lot of qubits. They couple to them, and there is a information. You want to keep the information only into your circuit, but that information is lost, to the environment, and we would like to minimize it. Although there is an improvement in the coherence time, in past more than 2 decades, good improvement, but still we are order of magnitude away to have a commercial scale quantum devices. So dielectric loss, we call it, say, TLS losses in the circuits. So we model it, all the noises, okay, in a circuit we modeled with this two-level system. So you can see it's like a qubit, two-level system. There is a transition, okay, from one state to another state. And these two-level systems, okay, can be anywhere in the circuit, okay, but because of defects at the different interfaces, you can see in different colors. Yellow is the metal-air interface, the red is the substrate-air interface, and there is a substrate-metal interface in green color. So these three interfaces, okay, has more TLS, okay, and it's more important over here. They can be anywhere, okay, but if their density inside is a little bit more, they are not that much problematic, okay, they are more problematic if they are at the surface. Their density is generally more at the surface. The reason is, okay, those who understand the materials, whenever you finish, okay, the material fabrication, you grow a thin film. At the top, the crystal structure is different as compared to the material. Further, okay, there is the material which you use, they have a very high tendency of the oxidization. Okay, silicon forms oxides, aluminum form oxides, niobium form oxides. So these oxides grow randomly. We don't grow them. So there is a lot of defects over there. So these defects are going to, okay, generate, okay, a two-level system. Okay, and these two-level systems are going to couple with our qubits, and they reduce the coherence time. So TLS density, okay, and the location is very important, because the coupling of the TLS, okay, to the a qubit depending upon, okay, the distribution of the electric field. Okay, so the location is also very important. Okay, so that's why when we are working as a material scientist, we look at the density and we look at the location. So even in a tantalum is a very new material, okay, and they observe, and Professor Fahd also mentioned it, the coherence time of the qubit is 0.5 millisecond. It has been reported just recently, but in that material also, okay, there is a defects and there is a effect of decoherence over there as well. So now the question is, how we will measure these defects? How we will detect these defects? Okay, so my areas, I will play with the materials, I will try to reduce them. Then definitely very next question is how you are going to measure it. How you make sure the TLS is reduced or increased, where they are, and so and so. So the resonator is a very useful device, okay, to detect and to check what kind of losses are in your quantum circuit. So I just simply use this resonator. This you can see in the middle there is a metallic strip. I put the lambda over there, the length of that resonator. It can be depending upon what kind of resonator you have, lambda by 2 or lambda by 4. So this resonator is a very useful device, okay, very useful component of my quantum circuits. I don't need any extra component to measure the TLSs. Okay, so the part of the quantum chip can be used to measure these TLS on non-TLS losses. Okay. Quality factor measurement is very, very high school physics nowadays. So you know that's how you define the quality factor. There's two types of losses, okay, in a circuit. It could be internal, it could be external, but my focus is only the internal one. Okay, I talk about the coherence effect, okay, from the material point of view, internal loss in the quality factor, and that you can measure it if you have the resonance curve. So using this simple formula, you can find out, okay, what is the quality factor of your resonator. So just simply, I take the resonator and I draw this experimentally. Okay, I draw this curve, and from this curve, I can find out, okay, how much is the quality factor of my resonators. There's some mathematics over there. Okay, I don't want to go to that one. So basically, the conclusion is, if you have a less dielectric loss, higher the quality factor mean, okay, higher is the coherence time of the qubit. This is simply the theory behind it. Now, as I mentioned, okay, resonator is a very useful test structure, okay, to measure the TLS losses, okay, because of its simplicity. It's just simply a metallic strip. You can fabricate it very easily, okay, and it can measure to a very high accuracy. It can measure, okay, the losses in a wide temperature range, okay, and in a wide number of photons. So this is a structure. Of course, Professor Irfan Siddiqui also mentioned it. I'm working in collaboration with him. So we're using exactly the same geometry of the quantum chip, and we modify the surfaces, and we look at it, okay, how we can improve the coherence time. So I play with this metal air interface and the substrate air interface. So in the past, okay, hardly 2 years ago, there was a concept, you cannot put anything at the metal-air interfaces. The idea was, okay, and I was a big debate with Professor Ivan, so 4 years ago, that I want to put the additional material. He said, no, if you are going to put the additional material, then it's going to create, okay, more defects, lattice mismatch, new material, more defects over there, more TLSs, okay? And he said, okay, no, we cannot put any additional material on the top of it. Then he come up with some new idea, and that I will talk about it very soon. So this is something I'm talking about, the debate with him 4 years ago. It took me 6 months to convince him, at least to try something, okay? And ultimately, I tried it, thanks to the COVID, and I will talk about it, how I started it. So before I go into the detail, as this Professor Fahd mentioned it, so we would like to see where these TLSs resides. Okay, although we believe in this thing, they are at the metal-air interfaces, substrate-air interfaces, and oxides, as I mentioned. Okay, there's not a crystalline growth, so mostly they are there. So this is something we did it, okay, in collaboration with Professor Fahd, okay, and the material expert in the LBL lab. Okay, they did really nice work. This is our joint project, and we tried to figure it out where those TLSs are. So clearly you can see, okay, there is a good thick oxides on the niobium as well as on the silicon. So what we did, that generally we do, we etch, okay, the substrate. That's a very common process in microfabrication process. Okay, we etch the substrate for 0 second, 30 second, up to 1200 seconds. So with this etching, we were able to get rid of the oxides. You can see over here, okay, with 1200 seconds of etching. So we have a minimum oxides on the silicon and the niobium. So these oxides thickness also measured with XPS. And finally, we did the quality factor or the loss measurement. So clearly you can see, okay, in this middle graph, okay, the loss decreases, okay, as we get rid of the oxides. Okay. Now you can see in the middle graph, okay, when you are at 10^6 or 10^7 photon, okay, this the loss is almost the same. But this particular range is not useful for us. 10^6 mean in my cavity, in my circuit, I have 10^6 photons, okay, on average. This is not a useful domain. When I want to process the information on my quantum chip, okay, I need a single photon. So 10^0 is my domain. I look at the quality factor in this particular range. So, but of course, it's a chip, you do the measurements, okay, you have to do multiple steps, and you have to expose the chip to the environment. As soon as you exposed it, oxides regrow. Okay, but this experiment tells us, okay, the etching oxide, these TLSs resides, okay, at the metal-air interfaces, and particularly in the oxides. But this particular solution, BO etching, is not a sustained solution. Okay, we want this improvement of the TLS, okay, permanently. Now, okay, not in 2020 or 21, in 2024, there is a lot of work putting a capping layer. Okay, so this is the work, they put the ruthenium, okay, onto the niobium, and they were able to improve the loss, they were able to reduce the losses by a factor of 2. This is not the only paper, I will just simply go over it to give you an idea. The capping layer, in first 2 decades, no one tried it, because theoretically they thought, if you're going to put additional material, lattice mismatch, additional material, there will be a more defect. But experiments are showing something different. Another paper, you can see all of them will be from 2024. They put the TIN onto the niobium, and they observe, again, a suppression of the growth of the oxides, no oxides over there, and improvement in the quality factor. One more paper, they put the gold on it, okay, and they observe the improvement in the quality factor. There is another paper, they put the magnesium and the tantalum, okay, it's a new material, okay, just discovered hardly 2 years ago. They put the magnesium and they observe suppression of the growth of the oxides and improvement in the coherence time. Okay, gold, palladium, many papers, all of them are in last year, in 1 year, by putting the capping layer. Okay, so this is a little bit old paper, but they are doing some ion bombardment, and they are, by putting the ions on the top of it, they were able to reduce the coherence time. So, as I was talking about, when I proposed this, putting an additional layer, so Professor Fahd didn't agree it. Okay, I deal with these molecules. they grow on the substrate like your hair. Perfect monolayer. Because every hair has a one binding end. You cannot have that multiple ends, binding end. So I said, if additional materials are going to create more defects, let's put these molecules. And these molecules will not create any defect. Molecules homo-lumen gap, mean in the language of the 2LS, TLS of these molecules is very well defined. And they bind perfectly at the interface. If they are going to create a defect, that is only between one atomic layer. And this binding of these molecules with the surface is also very well defined. But it could be there is a defect, as you can see in the second picture, there could be irregularity. This is the simulation, but actually there could be some irregularities over there. So I said if you put these SAMs, then we can have control the defects. As soon as you fabricate it, put the SAMs, and there will be no further growth of the oxides. He said, no, chemicals, it will make my lab dirty. And always when I would talk to the physicist, any chemical, just, oh no, chemistry is dirty. It's a dirty process. We don't want anything new. Because he is basically making high quality chip, and he don't want to mess up with his fabrication process, and which I can understand it, because they spent decades to optimize that fabrication process. Luckily, because of the COVID, I got the chance in KFUPM. So these are the experiments. First, I tried in KFUPM, in a dirty lab. I was able to fabricate these resonators. So what I do basically is, before I go to the detail, SAM is a very known to play with the surface chemistry. People are using it in many different areas, particularly in biology and chemistry. You want to play with the surface chemistry. These SAMs is almost more than 3 decades. The scientists are using it for different purposes. But particularly, there's something which is convinced me it can be used to stop the oxidization process. So I thought if you can use it to minimize the oxidization, I can use it. My purpose is completely different. But no one used it before me, in superconducting circuits. So it can be used for, the fabrication of the SAM is very simple. You can do it by CVD, you can do it by evaporation. And the simplest possible technique is you have the SAM solution, just like you put a salt in a water, SAM solution, dip your sample for 10 seconds to 10 hours, SAMs will be there. Time I need it just simply to have the good coverage and the regular coverage. Otherwise, 80% of the coverage, with some defects, I can get it in 10 seconds. So the SAMs have been used to control the chemical properties, have been used to control the work function, insulate. People are using it for gate electronics, nowadays in a smaller electronic structure, there's a leakage current issue, they're using it SAM to control this one, and most important, they're using the dielectric properties. This is something which basically additionally, probed me that let's try it in the superconducting circuits, because these dielectric properties are responsible for the loss. So that's why, suppression of the growth of the oxides, and it's reported theoretically, experimentally, the control of the dielectrics convinced me, let's try in a superconducting circuit. So that's exactly what we did. We made these resonators, and we put these SAMs on it. And after putting the SAMs, it suppresses the growth of the oxides. We did some measurements, and we observed there is a decrease in the growth of the oxides because of the SAM. And we thought there will be some increase in the quality factor of these resonators. So we use exactly the same chip. So you're familiar with this design. And what we did, we put the SAM at these 2 interfaces, metal air and the substrate air interfaces. And we did the quality factor measurements. First we did, whether SAMs is there and it is suppressing the growth of the oxides. We verified it with XPS data. And then we did the quality factor measurement, in the Professor Irfan's lab. So we are not making anything dirty. So everything is fixed on the chip, and we put in a dilation fridge, and we did these quality factor measurements, and we observed a really good improvement in the quality factor of these resonators. So, but one thing we observe, if you put the SAM at the metal substrate interfaces, there is a decrease in the coherence time. So there is an improvement over there when you put it at the metal substrate or substrate air interfaces. This is another study. We published these 2 publications. The thorough study, effect of SAM fabrication process and so and so. And when we put the SAM over there, so there is a decrease. And now, nowadays, of course, at KFUPM, we don't have the dilution fridge. So I just retuned my research a little bit. I saw, okay, it is now well known, oxides are responsible, okay, oxides are the host of the TLSs. So what I'm doing at the KFUPM, I cannot do the quality factor measurement, but my focus at the KFUPM currently is, okay, suppress the growth of the oxides and try to make sure, okay, SAMs are responsible for the suppress of the growth of the oxide. So no one tried, okay, any capping layer on the aluminum, and no one tried the SAMs on the aluminum, okay, for superconducting circuits. So I prepared 2 types of samples. One is exposed to the ambient condition, and other 2, I put the SAMs on the top of it. Then I did the XPS measurement, and clearly SAMs suppresses the growth of the oxides, okay? And this is just simply, okay, detail of the XPS. And further, okay, I expose those samples, okay, to the environment for 15 days. And I observe, okay, there is no considerable growth, okay, on the samples which are passivated with SAM with the oxides. Okay. So this is our recent results, okay, and we are not able to do the quality factor measurement. I did some other measurements also to make sure SAMs are there. Contact angle measurement is one option, okay, and I think so the time is over. I would like to, they are just simply the material measurements. Then we did the simulation also, okay. We had some experimental data, so we played with the different interfaces and we did the simulation, okay, and we did the quality factor measurement. Because of time, I cannot go over it, but I will strongly encourage you. My student has a poster over there, and he's talking about mainly about the simulation of these resonators, losses at different interfaces. So all these details, you can get it, okay, from the poster outside. And we did the thorough study, okay, we simulated all interfaces with different losses, different thicknesses. And finally, even we did the deep etching as well. So nice simulation work, my student did it. And finally, this is my conclusion. SAM applied to the aluminum surfaces suppresses the growth of the oxides, and we believe we can improve the coherence time of the circuits. And finally, I would like to thank, okay, Professor Irfan Siddiqui, okay, for this, because of his collaboration, because of his interest in collaborating with KFUPM, we were able to start the activity over here and working most of the experiments, okay, depending upon his facilities. I would like to thank my student, okay, Al-Ghadir, who did most of the experiment in the Professor Irfan's lab, particularly related to the quality factor measurement. Okay, Professor Fabrosi from KAUST, he basically allows us to fabricate these SAM samples in his lab very first time, and now we're fabricating in Professor Irfan's lab as well. And my student Umar Saleh and Professor Khan Alam. And finally, thank you very much. Yes. Yes, question? Yeah. He's bringing it. Just wait.
Thank you, Professor, for the insightful presentation. Actually, when I go through the presentation, I've got 2 questions. The first one, when you mention dirting or making dirt to the lab, so is it the manufacturing lab or the lab where you are testing your chips? Because in both cases, I think the lab should be prepared. So in manufacturing, there is a clear room, facilities, ISO 5, 7, or 3. And in the machine, I just wanted to know, there is some precautions or procedures in order to ensure that minimum noise will be achieved when we replace the chip. The second one is a technical one, because I'm curious about your research. How did you calculate the binding energy for some of the material? So is it estimated, or?
It's well known. With the, you have the STM study, individual molecule, individual atom. Yeah, there's a lot of literature available. Okay. It's a 30 years old knowledge of binding the SAM onto the surface.
All right.
Okay, so from 91 to 2000, SAM, okay, fundamentals are well defined. What kind of crystal structures, what's the binding energy? Okay, a lot of things are available in the literature. So I don't study, okay, the fundamentals related to binding of the SAM.
All right. So you replicate what
I
others...
replicate the process of this.
Thank you.
Exactly.
And for the first one, I'm interested to know why you mentioned
of course.
dirty.
I agree. Professor Irfan was worried about it. Of course, these additional processes can contaminate your process anywhere, because these SAMs can bind, they have some different kind of chemicals, and we are not chemist experts. Okay, for chemists, some things are very obvious, and something for us. Yeah, if you are going to introduce it in your clean room, the fabrication facility, you have to be careful. Okay, I will prefer to do it in a separate glove box, but from the measurement point of view, they bond it very strongly over there. There is no leakage possibility, okay, into your dilution fridge. Okay, fabrication you have to be careful, but not from the measurement point of view. Okay, we'll talk about it later. I think so the time is over. Thank you.
Thank you, Dr. Rao, for presenting. Now we'll have a 10-minute break before we go to the third speaker of the day.
انا زيك ماتيريال انجينير. انا
تبعتها بالايميل بي دي اكس اصغر. طيب هذه بس ناخذ ايميل الشبكه ايميل. ابعثني.
نايف. Three, two, one, test. ارفع شوي. Check. Three, نازل. Three, two, one, test.
talk of the day, Dr. Hammam Qasim will be presenting overcoming roadblocks, the future of quantum computing with superconducting circuits from Keysight Technologies.
We can get started. My name is Hammam Qasim. I am with Keysight Technologies. I am very proud to be here. I wanted to start by thanking the organizers for inviting me here. I'm from Saudi Arabia, but this is the first conference I attend in Saudi Arabia. Now, as you can see, the topic I picked for my talk is very ambitious. I want to talk about the future of quantum computing with superconducting qubits. And I want to tell you all about it in 20 minutes. So it's going to be a little bit tricky. And also I'm following after Dr. Irfan's talk, which more or less covered the same topic I'm going to talk about. So it's going to be tricky for two reasons. But I think I have some interesting perspective on this question. And we will look at slightly different things from what we saw in the first two talks. Okay, so I want to start by talking about this huge historic milestone, in my opinion. Late last year, Google released this announcement where they basically announced that they have constructed, or they have demonstrated, a quantum memory beyond break-even. So what does that mean, a quantum memory beyond break-even? Well, it just basically means it's a, what that means is that it's a quantum memory that can, that essentially outlives the best physical qubit that it's made of. So when you want to encode your logical qubits using quantum error correction, if you want to encode the information using some redundancy, you use a whole bunch of physical qubits to encode, let's say, 1 or 2 logical qubits, you have to use a lot of extra circuitry, a lot of extra gates, a lot of extra qubits and measurements, and the whole thing just gets a lot more complicated. And each one of these elements introduces noise. And so naively, you would think that by adding all that noise, well, not naively, but what has happened so far up until this historic milestone was that when people did that, they ended up getting worse fidelity than they started with. So they would go through all the trouble to encode a logical qubit, but then find out that it's actually noisier than the physical qubits. And this is basically the first time that we were able to see a logical qubit that, well, let's say in the surface code, that outperforms all the physical qubits that it's made of. And this kind of, settles a big, if you want, this is kind of a big story arc that was concluded with this announcement. It goes back 30 years to the first quantum error correcting codes by Shor and Steen. So people knew for the past 30 years that this is possible, but it took all that time just to demonstrate it. And it was really this discovery in 1994, this purely theoretical discovery, that spurred interest in quantum computing. Prior to that, since the 1980s, after Feynman made his suggestion that we could use quantum systems to simulate quantum systems, serious physicists knew that is an interesting idea, but it's not really possible because the degree of control and precision we have to have over the qubits is just ridiculous. And so we can't really do it. And it took all this time, all the 15 years roughly until the breakthrough came and people found out that actually nature allows you to do that. It's actually possible. There's a hidden method to do it, which is called quantum error correction. Okay. I will not say much about the threshold theorem, but it's basically the theorem that makes all of this precise. It accounts for all the little details and all the tiny little things that were not covered by the original error correcting code proofs. Okay, so we have this historic milestone, but where do we go from here? What is next? And I want to highlight that it is actually not very clear where we go from here, because there's a few problems that are standing in the way between us and scaling up this technology. So let's take them one by one. First of all, it's just a quantum memory, and what that means is you don't do any logical gates, so you don't actually perform a computation. All you do is just encode a state and then look later at the state and verify that it is the same, that it hasn't changed. But from the technical perspective, what's really kind of worrying is that this experiment does not require real-time decoding, even though they claim to have done real-time decoding. They do not do it in a feedback manner. So they only have a classical process running in the background, kind of at the same pace as the QPU, keeping pace with the QPU and decoding the measurement outcomes. But it doesn't actually feed back into the system, which is a huge step in quantum error correction. So if you can't feed back reliably into the system and with low latency, then quantum computing, the fault-tolerant quantum computing is not going to happen. So we can't really extrapolate from this result directly. We still have to see what people come up with when it comes to real-time decoding. Another issue is that these errors are, so even though they were suppressed, they're still quite high. They're not yet at the regime where we can do any meaningful computation. And more, so I'm talking here about the logical error rates. They're not low enough. The physical error rates, they have been more or less the same since 2019. So there hasn't been any major improvement on this device since 2019. And maybe the biggest obstacle or the biggest problem is what people have referred to previously as the tyranny of the wires. So if you look at this is the Willow chip, the Google chip. It's tiny. You can hold it in your hand. But if you look at the entire device, it's massive. It has all of these wires. So this is the cryostat, open cryostat. You see all these wires going in just to control the qubits. It's really hard to point with this thing. So you need hundreds of coax cables to go into the cryostat. You need so that increases the the thermal load on the cryostat. That introduces it introduces a lot of complexity. Things can go wrong, crosstalk, miswiring, all sorts of problems. You also need a lot of microwave circulators, which are bulky and take up a lot of space and dissipate heat. And outside of the cryostat, you need a lot of you need multiple racks of instruments just to perform the control and readout. And it's really hard to see how this can be scaled. So before I talk about, okay, so my plan for this talk, I'm trying to go backward, but it keeps going forward. My plan for this talk is to essentially give you a quick overview of recent progress, recent experimental results that try to tackle some of these problems. So these are the things that we should keep an eye on, because a breakthrough in one of these regions can, in one of these research fronts, could really mean that it can be the next big thing. And if we go back to this historical timeline, the discovery of the transmon was a huge, it was something that enabled the technologies of today. And so, error correcting codes were nice from the theory perspective, but from the device fabrication perspective and device design perspective, qubit design perspective, the discovery of the transmon qubit was, instrumental. And so we want to keep an eye for something like that, a big technological breakthrough that'll take us from where we're at right now to the next level. So I won't talk about the transmon qubit because it's been covered quite extensively in the previous two talks. But yes, I can't resist, I guess, when I see the slide. It's an LC circuit with with a nonlinear inductor, single qubit gates, and 2 qubit gates are done using microwave and flux control, and then readout is done dispersively. So this is technically not all the transmon qubit, but this is the standard way that qubits, superconducting qubits are designed and are scaled up in today's QPUs. There's 2 different ways to do it. I guess I'm not trying to compare Google and IBM, but roughly speaking, I am comparing them, or comparing two different approaches. So Google have tunable couplers and tunable qubits, and this allows them to do fast 2 qubit gates, and it allows them to do, to have essentially, to be able to calibrate the qubits post-fabrication to avoid things like frequency collisions. And for that reason, they have, very high 2 qubit gate fidelities because they have tunable couplers and tunable qubits. But it's also for this reason that they have low T1 and T2. The idea here being when you introduce flux tuning to the system, you introduce an extra noise channel. And so you introduce another source of decoherence. IBM, on the other hand, they used, or at least until recently, they've been exclusively using fixed frequency transmons. And there, they have very high T1 and T2, but their CR gates, their cross-resonance gates, their entangling gates, are too slow. So they take up to 500 nanoseconds to do a cross-resonance gate. Moreover, they have to restrict the connectivity to avoid the problems with crosstalk and collision, frequency collision. Okay, so what are some of the challenges? I've written out 5 different categories here. I'm not going to try to go through these in detail, or I'm not trying to claim that this is an exclusive list of challenges, but I just want to quickly touch on each one of them. Coherence and error rates is a big one. From the error corrections perspective, fault tolerance requires us to have a constant error rate as we scale up the technology. So as the number of qubits is increased, we have to keep the error per qubit constant. If you don't have that, when we scale up, the qubits become noisier and noisier, then it's hopeless. We're not gonna reach fault tolerance that way. But on the other hand, when you have more and more qubits, that most of the time introduces extra noise, extra sources of noise and extra noise channels, which complicates life quite a bit. There are fabrication challenges from the fault tolerance perspective. Also, we need fabrication to be uniform. So one of the assumptions. So even if you have a good average error rate, we want it to be distributed equally among the chip. We don't want some part of the chip to be very good and then some parts of the chip to be noisy. That'll mess up with quantum error correction. It'll mess up with the threshold theorem. And that is a problem from the fabrication perspective, because assuring that you have consistent fabrication if you have a very large device is pretty hard. It's pretty hard to guarantee that. There's also material defects in fabrication and precision, which overall just degrade the quality of the qubits. There's also architectural challenges. If you want high connectivity, which are needed for some quantum error correction experiments, then you need then you might introduce extra crosstalk, and you might have increased wiring complexity on the chip. The big problem, one of the big problems is control and cryogenics. So just the infrastructure, the instrumentation that we need for control and readout is just ridiculous. It's unscalable, and it's hard to see it going. It's hard to see that problem going away without a major innovation. Finally, for quantum error correction, we need to do things like real-time decoding. So we need to be able to process the measurement data that comes out of the quantum computer in a streaming fashion. We need to be able to do it as it comes. We can't allow the information to aggregate in the classical processor, because then we'll run into something called the backlog problem, where essentially we can't keep up with the quantum computer. We can't decode in real time. And then we have to feed back. Once we've decoded, we need to feed back. We have to do it fast enough. And moreover, there's a huge overhead for quantum error correction. So, okay, I have only a few minutes left. I'm going to quickly touch on some ideas and point you to some references for things that we should keep an eye on as we scale up this technology. So, better qubits, better gates and better readout, cryogenic control, and better error correction. Okay, for better qubits, I want to highlight 0-pi qubits. I think Professor Siddiqui touched on them very quickly. They're topologic. They have intrinsic protection. They can reach lifetimes of milliseconds. Sorry, of tens of seconds, actually. But reaching that regime is really difficult. Kirkat qubits, they also have intrinsic protection, but unlike 0-pi qubits, the protection is only along one direction. So they only have protection, let's say, from bit flips, but not from phase flips. Nevertheless, they can reach very good coherence times, very good lifetimes. So in a recent paper by Hajar and et al. From Professor Siddiqui's group at Berkeley, they reached a coherence time of 1 millisecond for X-type noise. Better gate fidelities. So these two papers are from Professor Will Oliver's group in MIT. And they were able to do extremely high fidelity CZ gate, 3 nines in 15 nanoseconds, using a novel architecture where they couple 2 fluxonium qubits using a transmon. They can also do single qubit gates very well. Fast readout, up to 5 nanoseconds. This is from MIT as well, Kevin O'Brien's group. Cryogenic control. Here's a paper from IBM where they put all their control electronics in the 4K stage, and they're able to do single qubit gate and 2 qubit gate with decent fidelity. So this reduces, this is one of the approaches for reducing the number of wires going into the cryostat. Okay, quantum LDPC codes. This is an approach taken by IBM. What they want to do, essentially, is, so quantum LDPC codes are like the surface code, but they have a lot less overhead. You can use a lot less qubits to encode a logical qubit for this, at the same error rate. So if you want to encode a logical qubit at some fixed error rate, you need much less qubits using quantum LDPC codes, and not just asymptotically, but in the physically practical regime. One example was reducing the number of qubits from 3,000, the number of physical qubits needed to encode 12 logical qubits, from 3,000 to only 280. So that's a huge saving, but it requires, so unlike the surface code where all the parity checks are local, here you have non-local parity checks. This paper by Bravi and others in IBM basically finds a way to do it using only a biplanar topology. So if if you imagine having two local, two planar graphs for the qubit connectivity, and you just overlay them on top of each other, you're able to implement this code only for a quantum memory so far, so no logical operations, but with huge savings. And that's why IBM is seriously pursuing this multi-layered architecture where you have different circuit elements residing on different surfaces of the chip, and they're coupled together through silicon vias. So this can accommodate long-range non-planar connectivity, and ideally, in the future, it can give rise to actual physical implementations of these quantum LDPC codes, which are much better than the surface code. So this will reduce the number of qubits needed, and therefore, it will indirectly tackle a lot of the problems that we talked about. So the number of wires going into the cryostat will be reduced, for instance, for a given application, for a given problem size. Okay, Google is looking into ways to get rid of magic state distillation. So we're going to do a magic state cultivation instead. I'll just refer you to the paper because I am really out of time, and I should probably wrap up. I just want to talk quickly about real-time decoding. Like we said, the problem in real-time decoding is that we want to process the measurement results, which for a superconducting circuit usually happen once every microsecond. So what I mean is the rate of measurements is about 1 per microsecond. So you need your processor to operate with a pretty high frequency. It needs to process the data very quickly, and then it needs to be fed back into the system. Here's a couple of papers from Riverlane where they tackle that problem. In the first one, they come up with a parallel window decoding method and show that it's the only scalable method. Nothing else will be scalable. And in another paper, they introduce a new decoder, which they implement on FPGA and on ASIC. And they tackle fairly large qubit sizes. Okay, in conclusion, significant challenges remain, but cutting-edge research will likely provide the answer. We should keep an eye on the big companies because they are, they have distilled they have at their sites what they think is a big breakthrough. They're looking for that big breakthrough, and so it is likely to come from there, or from academia. Who knows? But we should keep an eye for a big breakthrough. And with that, well, okay. Before I wrap up, actually, I want to shamelessly promote my employer. So I am working with Keysight Technologies. We have presence in Saudi Arabia, and we are increasing that presence. Our two major products for quantum computing applications are quantum EDA solutions. So this is electronic design automation software for simulating qubits. So if you want to design qubits, this is a very good way to simulate them and extract things like the qubit frequencies, current nonlinearities, and cross nonlinearities. Cross curves and self curves, etc. So you can extract quantum parameters fairly nicely with this software. It sits on top of Keysight's EDA for solving electromagnetic problems. And we also have the world's first 1,000 qubit control system. It employs, it uses the best hardware there is. Keysight's well-known AWGs and digitizers and down converters, all packaged together in a way that's easy to use, with some very nice specs, and with large-scale quantum computing in mind. So if anyone is interested in any of these products, please talk to me afterwards during the break. And with that, I would like to thank you.
Thank you, Dr. Qasim, for presenting. Now we're going to go for the fourth talk of the day by Dr. Ahmed Qattacha from IBMQ, Redefining Material Science.
Thank you very much. Assalamu alaikum. Thank you very much for giving me this opportunity. And please accept my apology because I lost my voice during LEAP. So I hope that you can hear me. I'm so thrilled to be here. And unfortunately, I was unable to upload my slides, so I will go with the PDF version. And please feel free to interrupt me, ask me any question about my presentation. So let's start. Next slide. Guys, all right. So let's start. Basically, I'm going to cover today. Can you go to next slide, please? Oh, perfect. All right. So basically, I'm going to touch base today with giving you a glimpse or just the flavor about our research on corporate level and on personal level. And then I'm going to cover some talks about why do we need supercomputing for material science, why quantum, and why now. And then I will give more time about talking about a new concept, quantum-centric supercomputing, and have your views about it. And I'm very excited to talk about this latest advancement in material science. So quantum in IBM sits under research. We are more than 3,000 researchers across the globe, and I'm so lucky to be managing a vast region, Middle East, Africa, and Turkey, but based in Riyadh. So I'm sitting next door. I'm so excited to be there. And the research that we are conducting covers too many areas related to computing. So you can say that we are covering cloud computing, artificial intelligence, quantum, superconducting, and more. We have a great heritage of discovery in many areas, so more than 77 years. And amongst our colleagues, we have 6 Nobel Prize laureate and many distinguished engineers and IBM fellows. So speaking about me, so actually when Dr. Muhammad asked me to deliver a presentation in this esteemed forum, I was thinking about how I can share with you my career and share more about the research that we are conducting in quantum. So starting talking about myself, I wear, as you can see, more than one hat. So part of me is a chartered engineer, so I'm doing engineering, or I used to do engineering in micro and nano fabrication. The other part is material science, where I conducted many research projects in different areas, including healthcare, space, and defense. And the other part, maybe which is hidden, is I used to work in consulting, and I used to work in different industries, like automotive and in fabrication. So talking about my research area, so maybe the slide is jammed, but there was a nice video about the research area which I'm conducting. So basically what I'm doing is I act like a tailor. So if you want to have a suit, you go to the tailor and ask him to tailor-made a suit for you. So we, as material scientists, we tailor-made innovative materials based on the properties that you are asking us about. So maybe some customers wanted us to develop superconducting material, some other wanted tough material. So based on the application, we do our tuning of the properties and switch properties based on the application using some interesting algorithms or approaches. So, talking about material science. So, long time ago, material science has been considered as magic. And I still remember the time when I was in school, when I hate chemistry because it doesn't make sense. So there is no one general rule if you go to the periodic table. So speaking about electronegativity and all that stuff. So I gave up at that time. And then during my research, really I discovered that making research in material science is so fascinating. So at the beginning, as you can see, that material science started like a magic. So you mix different material together, and then you don't know what is the result. And during the 60s up to 1950s, there was some development or advancement in science where too many laws were discovered. And after the discovery or the quantum mechanics era, and the computational modeling and simulation era. In 1950, we have seen a lot of computational modeling or algorithms, as well as advancement in the hardware, in which we started to get to know more about materials properties and use them for our advantage to develop or manufacture new materials or novel materials or smart materials. And then after 2000, with the AI big data thing, we started to build databases and use these databases to our advantage to predict the properties and start to innovate, bringing a new material to life. And after 2020 and onward, this practice has been more structured. So we add Gen AI, big data or massive data, as well as adding quantum to the equation and discover some or explore the uncharted waters of material science. So basically, why do we need computational modeling and simulation? So as Dr. Arfan in the morning said that the discovery of new materials or new drugs require a lot of investment. So going the traditional way, we need to wait based on the cycle, approximately 20 years, to finish the approvals, the experimental work, going commercial, and all that stuff. But with computational modeling and simulation, we can get different properties of the material. So going from macro to nano levels. So at the macro level, maybe we are interested to get to know more about the structure of the material or the properties, the macro properties, like, for example, strength, stress, strain, and whatsoever. But going in the nano level, we can know more about the atomic structure of materials. And in order to do that, as you can see, that the more we deep dive, the more the computational cost will be, and the accuracy will be less. Why is that? This is because of the size of the computation. So we need classically more bits. We need more computational power. We need more energy in order to converge or get what we need. Speaking about the nano level, so the nano level went through a journey. So we started at the beginning by simulating or accepting the approximity of applying Newtonian mechanics to the atomic scale. So that was the promise, that using Newtonian mechanics, we can get an approximate results, which we can prove in the laboratory. But then with the increase of the computational power, we started to see different models. So we get into the atomic scale using, for example, Hartree fork approximation, then moving to DFT, and after that using more precise algorithms or approaches, CCSD and MP2 and moreover. But as you can see, the more we are getting into more accurate results, the less atom we can simulate or do the computational modeling. And also there is a limitation of the time that we do the simulation. So it's in femtoseconds. So these limitations made the researchers focus on bringing new algorithms. So speaking about the properties, so what interesting properties we can get in the atomic level. So in research, as a tailor, so some of clients wanted to know whether if we mix two atoms together, that there is a high possibility that they will interact in a way or another. And because we wanted to mix them on our risk without making an explosion, for example, or making radiation or whatsoever, we need to ensure that the reaction or the interaction dynamics is under control, such that when we conduct these types of experiments, it's safe and the results are expected. For some other researchers, we need to know what is the atomic structure. So how the atoms set with each other in terms of bonds. And in some other cases, we wanted to know, for example, more about energy, binding energy, surface level energy, and all other energy. And in some other applications, especially for superconducting materials, we wanted to understand the orbital structure or the electronic structure, talking about how we can increase conductivity of such material using some other techniques. So after that, there was a lot of debate in material science and chemists and physicists about what is the best way to simulate, to understand more about nature. And there was a debate where people think that, look, because we can model the reaction on the atomic level using Schrodinger equation, and Schrodinger equation is a quantum, so it's better to simulate or make a computational modeling using a machine that follow these rules. Some other people say that, look, nature is one. No matter how many lenses we are using, whether it's the physics, chemistry, or quantum, at the end of the day, we have one nature. And that was the motivation behind doing quantum computing. So these slides, I decided to add them just to give you, for non-quantum based researchers, more about what we believe is quantum computing. So quantum computing is a new paradigm. It will not replace the classical computing. What we aim is to go hand by hand with quantum, with classical together, in order to explore new areas where we currently cannot compute or explore, or in areas where we can need ages or hundreds of years, if not thousands, in order to explore. So basically we are using the fundamental properties of quantum mechanics in order to apply it for quantum computing. So these properties include superposition, entanglement, and interference. And I believe my colleagues, they have explained what do we mean about these properties, but I'm interested in showing the impact. So in superposition, we can achieve the exponential or polynomial power of the computation. Entanglement increase parallelism, such that we can evaluate the solutions altogether every step that we go through the level of the gates or the unitary gates that we are progressing. And interference can help us in optimization. So in a nutshell, quantum computer or quantum computing is a new paradigm for computing. It will help us to encode more data, and it will help us along with classical approaches to do more interesting use cases. So this is a summary with what I have already explained. So by no means we're not going to replace classical computing, because it has been there. They've been doing nice in some use cases. In some other use cases, quantum computer can go with classical computers hand by hand to navigate and reach or explore uncharted waters for some use cases. Now, speaking about use cases, so in research, in IBM research, we've been exploring many areas for quantum computing. So as you can see, we have explored the three main current applications for quantum computing, covering optimization, computational modeling and simulation, including quantum machine learning, as well as search and optimize. As you can see, so the application, the explorer of these applications covers different areas, including, for example, manufacturing, financial services, energy, and healthcare services. And quantum computing, the investment in quantum computing is huge. So there is a lot of investment in terms of money and capital and talent in this domain. And we've seen that the intention of government is increased exponentially. So as you can see, this is a study conducted by BCG, and they are expecting that the customer, when they say customer, it includes government and some interesting or interested entities in banking or in industry or space and defense. So it's expected that their investment to be 48 CAGR compound annual growth rate, which is really massive. And they have seen that this investment is not only in universities or in research. It includes companies, startups, the whole ecosystem as a whole, in order to get prepared before we reach the fault tolerance. All right, so what I try to do is to cover the material science part, why quantum is important and why it's important for material science per se. And then I will start to talk about supercomputing. So supercomputing as a concept is not a new concept, and even the high-performing computing is not a new concept. So we've been saying that this concept has been developed through years. So for example, the first milestone was the CPU. Actually, I left the best to the rest, to the last. So CPU, and then we moved to vector machines, parallel memories, and then we moved to GPU. And we believe that investing in QPUs along with GPUs will get us to what we refer to as a quantum advantage, because we have different approaches from other researchers or other companies to define what is meant by quantum advantage. So basically, this is the domain that we believe that the existing technology will help reach the quantum advantage. And let me just pause for a while just to explain what we mean by this graph. So as you can see in horizontal, this is the number of quantum gates. So in terms of quantum gate, the more we have quantum gates, the more we can do more complex algorithms. And on the vertical, we have number of qubits. And we as a company, we have reached the 100 plus qubits, which we refer to it as quantum utility. So this means that if you are doing anything less than 100, this can be done by a simulator. So you may, for example, invest this to build the capability, but in a quantum, you will not get the quantum advantage or start to see the advantage anything less than 100. And also, you need to consider that when you build your own circuit, you need to make it deeper in order to do more complex algorithms. So for example, if we map the famous Shor algorithm to this slide, or to this X and Y graph, we can see that in order to do the Shor algorithm, this will take us ages because we think that we need more gates in order to do more complex computation, and we need more quantum or qubits. But the promise is that by investing more in algorithms, there is a high possibility that we can push Shor algorithm from left to right, making it require less circuit and less number of qubits, and getting actually an acceptable results showing the quantum advantage for this particular algorithm using the noisy machines. And if we implement the same way of thinking by mapping the most interesting use cases now and start to map them to number of expected number of gates with expected number of qubits, we can see that the challenge is still there. And if we wait till we reach this number, it will take us ages. So what we believe is to speed up the quantum advantage, we need to work in two ways. The first one is to increase number of qubit beyond the utility area, beyond the utility era or area here, and invent, working with algorithm researchers to invent new algorithms. So in this way, we can speed up reaching the quantum advantage, which we are expecting to happen in 2 or 3 years. And once we reach this quantum advantage, we can pave the way to other applications in which we can put the device that we have invented in a commercial use, reaching fault tolerance in less than 5 years. So, how we can implement what I have explained in material science. So, in classical material science, do you want me to pause? If E4 is 2, will require us ages to compute. If we are using traditional ways, with GPUs, we can do it maybe in less than 1 day. But implementing this in quantum and transforming this structure into a Hamiltonian, as you can see that this structure includes 6 or 7 million Pauli operators. And if we approach them in the traditional technique of quantum computing, it will take us even more than classical. So the algorithm that we have developed and implemented with the collaboration of Riken University was novel. So what we are trying to do is, if you allow me to explain that, we encode the data using different encoders, and then we start to do sampling of some of the circuits, and those samples, immediately after measurement, we plug them into the Fugago supercomputers. And the Fugago supercomputers start to diagonalize them, and then we reiterate till we reach the optimal. This approach, using quantum machines with superconducting material, has led to actually amazing results, approximately best to the best numerical approach, which is the CCSD, in comparison. And this represents really the current future, not the whole future, because in future, in theory, we will reach the fault tolerant, we will reach the result, but this is just a step in order to reach the quantum advantage, using it to show a useful case of using quantum with supercomputing. I'm done here, and I'm happy to take your questions, and thank you very much. Any question? Yes. If I got your question right, so you want me to highlight how we can speed up the adoption or speed up the computation, the prediction? Okay, so I will talk from my company perspective. So we in IBM, we think that in order to increase the efficiency or the performance of the quantum machine, we need to look into 3 areas. So the first one is about the quality, and the quality is measured with different KPIs. So one of them is fidelity, one of them is T1, T2. So there are different, but as a user, you need an accurate or semi-accurate machines, which is one dimension. And we are working towards that by introducing currently error correction and error mitigation. We have reached the level of 10 to the power minus 3, and we're still working in terms of this is a high achievement in terms of number of qubits, which we have reached, which is 156 per QPU. The second is scalability. So in scalability, we have introduced a new technology calling coupler, because at the end of the day, you need to consider QPU like GPU. So you stack them together to do the computation. So our technology also is scalable, and this is another innovation or contribution to increase the efficiency. And the third one is the speed. Superconducting technology is relatively, comes with speed, because the coherence time is in terms of milliseconds or nanoseconds. So no matter, for example, if you do 1,000 shots, you can still get the results within time. And also we have published a paper, it's called the Bench Press, in which users can go directly and see how we can bench press the different technologies and see how they perform in different situations. I hope that I have answered your question. Thank you. Yes.
Development on that front for distributed quantum computing, is there a need for it? And if so, what are the advancements in that field?
So actually, in order to answer your question straightforward, so anything that contributes to speed up computing will be considered a high-performing computing machines or technique. So currently we're using GPUs with QPUs, get the benefit of both in some use cases or interesting use cases, and the Ricker research is one of example. And I myself, in my research, I use the parallel computing, but in a different way in order to make a comparison between what I can get from quantum plus classical and classical alone. So as a researcher, this is my answer. So I welcome any approach that can show me the accurate result, which can be validated in the lab for material science.
Thank you.
Yes, please. Yeah, can you go louder?
I'm talking about the example you did speak about in the last couple of slides.
Yeah, this one?
Yeah, so what properties have you
yeah, the binding
discovered
energy.
And what's, yeah, and
The
what's
binding
energy,
yes, the
and
binding
how do
energy.
they compare with respect to, so you said you compared the computation on
Yes.
classical versus quantum computing. So can you tell us, at least in the binding energy, what's the difference or the accuracy?
Yes, this is a great question. I will go fast. I know that we have limitations of time. So as you can see, in order to tell whether there's a binding or not, we need to have this notch. So this notch means that this is the lowest level of energy that we can reach in order to have the reaction. So nature tends to have the lowest, sorry. So nature tends to have or to reach any system to equilibrium, and the equilibrium is the lowest level of temperature. So actually what we try to do here is if we put two atoms away from each other. So that was the question. And then we start to make them close and then let them go away. So make them close and then let them go away. So at what distance we predict that a bond will be formed, and what is the energy? This is a classical computational modeling and simulation. So as you can see here in the bottom, we have the distance in angstrom, and this is the Hartree-Fock or the energy, and here is the lowest. So when we start with HCl model and restricted Hartree-Fock, it shaped well, but it doesn't give the exact temperature, level of energy. But when we compare the best one, which is CCSD, we find the quantum is going smooth with it. So this is how we gauge the actual. And of course, there is another way, is to conduct the experiment and take the measurement for this reaction, but it's very expensive and it's error-borne. So there is a high possibility for you to commit mistakes and don't get the right answer.
Have you done more complex computation, like absorption energy or something like that?
I personally or the company? The company, yes,
yeah.
and I personally, I did it, but I hadn't the honor to be part of this team. So this team is a great team. They conducted this experiment in Riken with collaboration with IBM research. But previously, yes, I did some nice research before I joined IBM. So these are examples. Yeah, offline. Yeah, because lunch is... yeah, and I'm more than happy to have any discussion offline with you all, you guys. Thank you very much.
Okay, thank you, Dr. Qudits, for presenting. We'd like to give him a small token of our appreciation for presenting. And then afterwards, we'll leave for a long lunch break. We'll resume at 1:30 p.m., inshallah. 1:15 p.m., inshallah. 1:15.
الطقة النظيفة أنا ما جبتها. جايب لي سندوتشات. جلخ جلخ جلخ. هاك أبو محمد. بتفصل انت؟ بتفصله ولا ايه؟ يا جماعه بتفصل.
كيف تشيل هناك في الكيف؟
وين؟
في الدعوة ولا في الكيف؟
الداوي هنا على الطاولة على الطاولة على الطاولة هنا على الطاولة.
لا لا عندي
इनको पता होगा ये कभी ढूंढ लेते हैं, ये सुन के पहुंचते हैं।
شوف ايش بك الحين؟ مشغول.
علمت على طول. علمت. جبل بحول بالضبط كده. على مش كهرباء شوي.
قطع هنا.
ولا شيء عندك؟
هذه القطعة.
استنى شويه شوف دقيقه دقيقه.
انا بجيب العيد ده بس من غير الشاشه اللي عنده ده لا ايوه بس ممكن تشتغل عني يا حاجه زي شفت كده انت معاك
عشان الكاميرا الصغيره اللي ايوه
والله لو انا قلت لك انا امبارح قلت لك هذا الشغل هذا رد من حاجه ما في وزول قلت لك ما في بعدين انت لما كلمتني لا انا في قلت والله بعد جيت راجع البيت الساعه 11 ونص مركز جيت البيت وما عندي ناجي بعدين وديني تو سيجنال انترفيرنس ان شاء الله اليوم.
طب خلينا نجرب على جهاز المشكله على جهاز تشتغل احنا زي حاجه هنا زي ما انا نزل ما نقول على جهاز على جهاز الصوت الصغير هذا وين هذا انا يا عم نزل ما نقول على جهاز ايوه ونزل الجهاز قبل يشتغل انا قبل يشتغل بالتالي كده
رايك شنو يا حبيبي؟
نجيب جهازنا ما نقول لكم بجهازنا والله عندكم انا جهاز ما مشكله
هو طالما حاجه ما بتاثر على شغلتك او وظيفتك انا طلع اما لازم توجيه غاز الهدوء شوف الهدوء بعد من بعيد والله ما البتاع ابو كهرباء دي معلقه وكهرباء دي معلقه
ايوه ما قلت لك خلينا نركب احنا اللي هنا وبعدين نقول لهم
ابو كهرباء دي معلقه ابو كهرباء معلقه
دقيقة قبل ما تودي اعمل التست هنا عشان
بس بص انا نشوف الشاشة عايز تشتغل ولا لا قبل ما نعمل اي شيء بعدين انا بمشي للراحة لانه كلمة
لو كم يوم بيقول لي يا لا الدرون انا وقفت الدرون يا اخي شغالين ورينا الثمن طيب انت هذول بيجيب الدرون يكون قاعد يقعد لي شهر بيرجعوه وبعدين انا ما بشغل لي في دول ثاني يا ابوي يقول لي درون بغرام كده ما بشغل لي في دول ثاني يقول لي درون بيجي اللي قال يعرف الدرون ده بشركة والشركة ونشتغل عليها نطور الشاشة يشتغل دقيقة خليه يشتغل لابتوب الماك ولا اي لابتوب؟ بعدين واحد بيتكلم عن شنو؟ ده؟ كل هنا بس كل هنا عندك
غصب علينا بنزلين معاك هنركب مع بعض سليم استاذ
شغلتوه حطيته هو ما بدا ما اصلا ما فصل البطاريه مع الضربه كيف الكهرباء ما كانت موصله هذا الكهرباء اللي جاي مع الاستخدامات ضربته هنا؟ تعرف الباور بيوصل معي انا بقول لك شفته سوى ومية طوالي ومية بس انا شفت كيف مش اسمه طيب الحين كيف بنتابع الموضوع ده؟ في لابتوب ثاني نحط على شو اسمه النت لا بسوي نفس الحركة عندي لابتوب ثاني عندك هنا؟ اختيارك؟ اللابتوب؟ خلاص كمل على الكيبل كده لما نشوف لك كيبل بعدين.
Hello? Hello?
هلا كيف حالك؟ طيب انا اعمل بس كلوزات كده شو تبقني 5 دقايق ولا دق لي زول خليني عندي بشبك على هذا والبش طالع من هنا اجيب لك الفلاش دقيقة الفلاش عندي جديد لا جديد جديد
have to figure out how to unmute it, though.
Okay, but I want to keep it here because I noticed that all the speakers, we don't have a monitor down here.
Unfortunately, yeah, it's
So all
not.
the speakers are looking sideways. So,
Look at this, yeah.
so I'd rather use this sideways than that sideways.
Sure.
Yeah.
I think this one is active now.
Okay. I think so. Yeah. Good. Thanks. Like this so that I can watch the screen because Okay. Okay. So you want to test this now? This sounds good. Is this good? Because hello, is this good? Because I'll stand here. Okay.
This clicker?
Yeah. Yeah. I tried the clicker earlier. Everything's working fine. Yep. Well, I tried it this morning. Yeah. Okay.
Okay. Now for our fifth talk of the day, Professor David Keyes is going to be presenting, where is it? The earliest arrival of quantum advantage. Please welcome Professor Keyes on stage.
مساء الخير. مبادرتي اليوم تتكون من جزئين. الجزء الأول بالعربية، الجزء الثاني بالإنجليزية. حسناً، الآن سنبدأ الجزء الثاني. شكراً. I would first like to begin by thanking KFUPM for hosting this and being the national leader in quantum computing education. I would like to thank Aramco for being the bold first national facilities provider in quantum computing. And I would also like to just appreciate being here and having the chance to interact with Mohammed Al-Sayari, who has just founded recently the Saudi Quantum Computing Association. So I think we're off institutionally to a very good start. If my slides come up, I will try to give a talk that's quite a bit different from this morning. This morning we had mostly physics. I'm going to talk about integration of quantum computing into supercomputing with an algorithms focus. I'm an algorithms guy and an HPC guy. I'm actually not a quantum expert, but I have a very optimistic view of what quantum is going to do for high performance computing, and I'm awaiting my slides. At the end of the talk, I'll invite any of you who are interested to join the quantum computing reading group at KAUST, where we have been working with NVIDIA's CUDA-Q educational unit. It's a 4-week course on quantum algorithms where you don't need to have quantum hardware. You program in a high-level language that back-ends to many quantum facilities or quantum emulators, including NVIDIA's hardware itself. So that's one way for people who are just getting exposed and don't have access to the facility to get involved. And I'll be referring to some other hybrid systems along the way where we have a precedent for quantum classical integration. Maybe before the slides come up, I can mention a few of those to save time when the slides do come up. There's a group in Poznan, Poland, where sorry. Okay.
Look, here, you could use the mic instead. Sorry.
Okay.
You can go like away from the podium so it doesn't echo.
Oh, okay. Are you going to give me my slides?
Yeah, and we're good against the size of channel. We're just having technical issues right now.
Well, one of the examples that you just heard about in the last talk was the work of IBM with RIKEN in Japan. There's also a project of QERA, the Harvard-MIT-based startup, working with the AIST, the Advanced Institute of Science and Technology in Tokyo, Japan. There's a project of ORCA with the Poznan Supercomputing and Networking Center in Poland. And let's see, there's another project of IQM, the Finland-based quantum computing startup, working with the LRZ, the Leibniz Rechenzentrum in Germany. These are 4 examples existing today where a quantum processing unit, 20 qubits or more, is integrated into a classical supercomputer. Classical supercomputers are needed to load the state and read the output of a quantum system, but more specifically, hybrid quantum computing refers to a back and forth, such as we heard some about this morning, where, for example, most of the work is done classically, but some portion of the computation, which is done exponentially more easily on a quantum computer, like finding the minimum energy state of a molecule, is farmed out. And this is very analogous to the back and forth between conventional supercomputing and GPUs. that we started to see in the year 2010 with the Tsubame supercomputer in Tokyo. And since that time, GPUs have steadily migrated into the supercomputer so thoroughly that they're now on the same node with CPUs, sharing common memory. And we anticipate that before long, the QPU will likewise be integrated, maybe not the cryogenic ones, you know, on the very node of the boards, but on a network that allows transparent access of memory back and forth. I don't know if I'm going to give my whole talk without slides. There's a lot of slides. Maybe I should wait rather than getting too far ahead of myself. They worked this morning. Mohammed, you just missed my introduction of your association. I think it was well received. If I brought my own laptop here, could we plug it in?
Technical issues. So let us take a break for 5-10 minutes.
Okay.
Sorry about that. We're going to lose your introduction. Sorry about the technical issues. Probably we're going to have 5 to 10 minutes break until we sort this out, and then we'll get back to the interesting talk of Dr. David. So probably 5 to 10 minutes.
I could probably go on further without slides, but
No, we want to see this. Okay.
somehow.
Okay, I guess this time the microphone's not working, but the important thing is that the slides are. So I hope I get to rewind, and I'll go quickly through the part that I verbally introduced, but hopefully I can get through my entire talk, which is about the earliest arrival of quantum advantage. And the purpose is to describe what I believe and what many believe will be the earliest practical use of quantum computing, where there is quantum advantage, what used to be referred to as quantum supremacy, what you heard IBM refer to earlier as quantum utility, and it is a form of hybrid quantum classical computing featuring a quantum-first paradigm, sort of a cascade from QPU to GPU to CPU that I will describe. And the purpose of this talk really is to be encouraging to look back at a very successful history from the 1950s to the present of the evolution of regular supercomputing and to see how that happened and how quantum computing can piggyback effectively on it. So the purpose of this talk is not to pour cold water on quantum computing. The purpose is to be more encouraging than looking at the physics limitations that we saw this morning. And I'll just, since I already mentioned this, this is not blue sky. This is an example where last November at Supercomputing, the Polish example was presented. Currently in Japan, there's the QERA collaboration. Currently in Germany, there's the LRZ IQM collaboration. These last two collaborations are, the entry point is about $40 million or euros to get a modest quantum machine into the actual machine room of the supercomputer. And then there's the one that we heard about from Professor Katacha about the RECON IBM collaboration, where they have 133-qubit cryogenic Blue Heron QPU. So this is what we're doing at KAUST. We don't have a quantum computer. We are friends with NVIDIA, and NVIDIA has a short course where they provide a programming model with back ends to some actual computer hardware, some of which is shown on the right, or to an emulator. And when we have our Shaheen 3 fully configured, it will be able to produce about, to emulate about 50 qubits, which is really quite a serious amount on conventional large number of petabytes of memory. So we are taking advantage of their programming environment, and you can too. And we're using it to explore primarily variational quantum algorithms. So I mentioned to some of our other presenters that I would be featuring one slide each on their work. You can already go hybrid in the cloud today at AWS. They have both quantum and classical machines ready to use in tandem. The French consortium Atos, which runs the supercomputer Eviden and the quantum algorithms group Colibri, has a hybrid combustion emulator. It's all done classically, but they're using quantum algorithms so that when the quantum computer becomes reliable, they can take advantage of it for the appropriate kernels. And this is a slide from IonQ, the Maryland-based company, claiming, and this is an article in Forbes, the future of computing is hybrid, why quantum computers will work alongside classical systems. And it's not simply to be the memory system for the modest memory of quantum computing, but rather it's for this back and forth where a computational task is partitioned into that part which quantum can do exponentially faster and thus save energy and time in a overall workflow. Quantinuum, another presenter here, has already been working on a hybrid solver with applications to the chemical industry. And interestingly, even though Quantinuum has its own hardware, their InQuanto platform, which is designed for material science, is also back-ended to IBM's Falcon system. And they have actually also done this partition on the previous slide, where the configuration, the molecular configuration is evaluated exponentially faster. But just to be sober about it, they've done H2 and Li2. They've taken the sort of the simplest two molecules in the periodic table as the limit of their ability right now. But of course, we'll be getting into ammonia and drugs and other things before long. So my quantum first philosophy is that quantum workflows will cascade. QPUs will be used wherever they have advantage, and their range of advantage is constantly increasing. GPUs will be used for everything that spills over, that has no quantum advantage, but has high arithmetic intensity with structured memory access, where GPUs are designed for, coming out of the convolutional things of neural networks. And then CPUs will take up the low arithmetic intensity, unstructured remainder. And this cascade will be quite challenging for computer scientists because we want to run many hybrid jobs at the same time on the same very expensive resources. So we will have to figure out ways of sharing these three different kinds of resources within a common memory space between jobs that don't necessarily use them in the same proportions. And that's going to be very exciting computer science. Now, why quantum first? Why should you always use quantum whenever you can? It's primarily, in my view, because of energy. Knowledge is now limited by energy in terms of our ability to use large language models for not just textual things, but image things and science things and so forth. Math theorems can be proved with large language models. And this figure, which was done 2 months ago by the US Department of Energy, projects data center use of national electricity budget in the US, which was running at about 7% growth rate until about 2017, occupying about 2% of US electricity, and then with the prevalence of AI in data centers began to take off, and when large language models began, it's now projected to grow at an annual rate of about 27% compound annual growth, and this is not sustainable. Individual data centers of 100 megawatts, which is sort of a hyperscaler typical center today, uses as much electricity as a city of 65,000 people. And many hyperscaler cloud providers are already going to the other, always far off technology, not just quantum computing, but fusion energy. The Helion Fusion Energy Company has promised to give Microsoft 50 megawatts of power for its small modular reactor powered data centers as early as 2028. So who will get there first, quantum or fusion? I don't know. I'm interested in both, and both together. The architectural affinities of HPC, namely simulation, analytics, and learning, are different for these three different computational technologies. But supercomputers of the future will use all three. They'll have maybe 1,000 qubits in a QPU. They'll have thousands of GPUs, and they'll have thousands of CPUs probably integrated on the GPUs, like the NVIDIA Grace Hopper and the NVIDIA Vera Rubin, which is on the roadmap now. And that will be the module that will be in Shaheen 3. The middle one is the AMD MI300, which is in the world's #1 supercomputer at Lawrence Livermore right now. And the top one is an image from Pascal, which is, of course, delivering the 200-qubit machine to Aramco shortly. And QPU will be good for variational quantum algorithms in simulation, the quantum Fourier transform in analytics, and quantum machine learning. GPUs, as I said earlier, will be good for structured data apps. They're very throughput friendly. And then learning, they're of course useful for training, and that's why their market has accelerated. And the unstructured data apps, that other portion of the computation with a lot of conditional statements and irregular memory accesses that doesn't go well on GPUs, that will be, that will be still on CPUs, but integrated into a common memory. And that's forecasted by Intel to be actually more efficient for inference than GPUs. So what should we do en route as mathematicians and computer scientists while waiting for the physicists and all the investors to give us reliable quantum hardware to hit quantum Moore's law? Well, we can research what to do with algorithms, applications, and doing the hard computer science of the quantum classical system integration. And we do have successful models. We have 40 years of CPU-based parallel high-performance computing since commodity parallel came on in 1985, and we have 15 years of experience with GPU, CPU, HPC, since GPUs added double precision to their visualization hardware in 2010 and were first used in HPC. So I've already seen this morning a couple of allusions to what's considered the first quantum computing algorithms paper by Richard Feynman. Interestingly, Feynman never mentions the word qubit. He simply refers to the atomic spins as calculatable engines. Qubit comes along in 1995, so we're in the 30th anniversary of the concept of a qubit, but we're still lagging reliable ones. The killer app for quantum algorithms was, of course, the prime factorization algorithm by Peter Shor, which is important because once quantum is reliable on this, RSA 2048, the world's most strict security encoding today, whether it's for storing data or sending data across the internet, will be open to all who have a sufficiently powerful quantum system. And so we're working, of course, on quantum encryption, which is beyond RSA 2048. But any company or country that's been storing encrypted data on their rival will suddenly be able to read it all when that algorithm becomes available. So that's really been the driver for $40 billion of international investment. Meanwhile, if you are scholarly minded, you can go to the quantumalgorithmzoo.org and you can read about 71 algorithms developed since 1982, since Feynman's paper, in a collection of 511 papers. This was put together by Stephen Jordan when he was at the US National Institute of Science, Standards and Technology. Now he's at Google. But luckily, this website has been maintained. And what does it have? I have 6 pages. I'm not going to talk much about them. I'll just mention, factorization by Shor. That is a superpolynomial to exponential speedup of prime factorization. We have the search algorithm by Grover, which is a polynomial acceleration of the classical search. We have the Deutsch-Sosa algorithm, which is considered really the first exponential speed up, and that is actually more of a stunt oracle than a useful engine for science or finance or something, but it's historically important. We have the linear systems of Harrow called HHL. That's a super polynomial storage, but don't be too encouraged. You don't get in the matrix equation AX equals B, you don't get all of X. What you get is the expectation value for some function of A on B. It could be, the reciprocal function, so you could get the mean of X or the max of X or something. But to actually get all the elements, you would have to run this algorithm as many times as there are. So it's not necessarily a winner for the most general kind of linear system. There's a group theory algorithm by Mosca, which is considered important. There is a matrix rank algorithm by Reichel, which is only polynomial. There are machine learning algorithms of varying speed up, depending on what kind of algorithm you're talking about. And there's quantum simulation, which is considered to be very good for material science and chemical reactions such as catalysis. There's simulated annealing, one of the earliest algorithms pioneered by D-Wave, which is a randomized optimization method. And that closes out this collection of known quantum algorithms that are better than their classical counterparts. So there's a lot of work to do in discovering more of those, as Ahmed said right before the break. So you'll notice on that slide there were 3 categorizations: polynomial speedup, exponential speedup, or super polynomial. And what they mean is the following. If the classical running time is designated C as a function of the problem size, for instance, it could be linear in the amount of data, or it could be quadratic or whatever, and if Q of n is the runtime of the corresponding quantum algorithm, then exponential speedup means what it says. The classical time is the exponential of the quantum time, or looked at the other way around, the quantum time only takes log of the classical time. The polynomial speedup, C, is proportional to Q to the alpha, where alpha is some exponent greater than 1. So if, for instance, the classical time is 2, then the quantum time is the square root of the classical time. And the super polynomial is interpolated in between exponential and polynomial. It's the exponential of Q to the alpha, where alpha is any number greater than 0. So if alpha were 1, we'd be back to exponential. But if it's between 0 and 1, It's better than polynomial, but not as powerful as exponential. And that's what those codes mean. And this is what it looks like for a linear algorithm. So we have the problem size little n and the complexity capital N, and green is a linear cost. And the blue line is an example of polynomial speedup, square root of n. And the dark blue line is an example of exponential speedup. They don't look very different on this graph, but quantum only becomes relevant for very large problem sizes. And by the time you push n out, there's a big difference between exponential and just polynomial speedup, and that will be reflected in a subsequent slide. So currently, quantum algorithm development vastly outpaces the capabilities of the architecture, but where have we seen that before? That was the case of digital computing in the 1950s. There were pioneers like von Neumann, who was talking about doing weather prediction and neutron transport. Oh, he only had, a bunch of vacuum tubes in his computer. But instead of taking decades to get to where high-performance computing is today, it may be simply a matter of years until quantum hits its Moore's law and enables all the vision that we hear about in this workshop to take place. So while we today have noisy, noisy, what is it, NISQ, quantum devices, noisy intermediate scale quantum, that's NISQ. Digital was unreliable once too. In fact, the great von Neumann wrote a paper in 1956 called Probabilistic Logics and the Synthesis of Reliable Organisms from Unreliable Components. In other words, how can we use computers that make all these mistakes and still get statistically reliable answers? And we are facing that same situation in quantum today, and we have the encouragement of having previously prevailed. So I'd like to call to your attention, and if you read one paper as a result of my talk, don't read Shor, don't read Feynman, they're very too early. Read this one from last year by a group from ETH and Microsoft, Thorsten Höfler, Thomas Herner, and Matthias Treuer, disentangling hype from practicality. What they do in this paper is they go through some of these algorithms and they compare them on an A100 NVIDIA GPU to the best imaginable quantum device that they can think of with very fast gate speeds and an indefinite number of qubits. And they basically show that because of the small amount of memory on a quantum machine and the slow memory access, that many of these algorithms that we just looked at may not in fact be able to beat their classical example for the size of problems that we are interested in today, largely because of the difficulty of getting information reliably in and out of the quantum system in a time less than the quantum system decoheres. So they actually don't see much hope for quadratically improved algorithms like Grover search, but they do, of course, for exponential improvement like Shor. And this would be a very good background article for anybody today. So let's set a baseline between us. What do we expect quantum to do before it becomes, before it attains an advantage? So this is a cartoon from Gary Larson. This is what quantum has to do before it gets to classical advantage. And let's look at 3 decades of HPC hardware evolution from the world's first teraflops machine. That's 10 to the 12th operations per second. I won my first Gordon Bell Prize on this machine at Sandia National Lab in 1999. It took nearly a megawatt, 850 kilowatts, and it occupied 150 meters squared of machine room space. Now that system is completely dwarfed by one single NVIDIA Blackwell chip, which you can buy for about $20,000. It's 30 times more powerful, from 1 teraflops, 1.3 to 40. It's 1/1000th time cheaper to power, 850 watts instead of 850 kilowatts, and it occupies 750 millimeters squared, so it has a 200,000 times smaller footprint. You can carry it around on your laptop if you want to. So this is Moore's law in action. Imagine a quantum Moore's law. Don't be discouraged by the physicists. We're going to see this happen. This is not vacuum tube stuff. This is some technology that we haven't heard of yet, but which our workloads will lead investors to back. So there are 12 elements of the digital ecosystem that have led us to where we are today. And I'd like to spend one slide on each of them very quickly as a challenge to quantum. I, David Keyes, challenge the quantum computing community to develop the analogous elements as the path to quantum advantage and the quantum first paradigm. And they are validation, verification, and uncertainty quantification. We don't just run point studies on HPC anymore. We vary the inputs to see how they vary the output, to have some knowledge about how accurate they are. We want repeatability, replicability, and reproducibility. Those sound like synonyms in English, but they are distinguished in the professional literature. We want standardization of tools, software tools. We want pre-competitive industry roadmaps, so the industry projects in one voice where we're going that help us plan applications and algorithms campaigns. We want discipline-wide benchmark problems from the applications. We want industry-wide performance benchmarks. We want a virtuous cycle that I'll explain in a bit. We want vertical tool chains. We want real-time immersion. We want physical modeling and performance modeling of the hardware. And we want something called hourglass and reproducibility, where one application's programming interface links many different applications to many different pieces of hardware. And we want convergence of the paradigms. Ahmed referred to the third and fourth paradigms of simulation and data analytics. We want to see those converging in the quantum world well. So I'm not going to go through these slides in detail. I'll just clarify a little bit what they are. Here's a journal from the Association of Mechanical Engineers, where they define what you have to do in order to publish a simulation in fluid mechanics or structural mechanics or plasticity or something. In fact, there's a whole journal that will accept papers on the technology of verifying that the results are reliable. So validation means, are we solving the right equations? And verification means, are we solving the equations right? And uncertainty quantification means, are we drawing a little ball of uncertainty around the inputs and seeing how big that ball is when it comes to the outputs? And we need to be able to do that in order for computations to be trusted. The Association of Computing Machinery has a reproducibility badge in 3 levels. Repeatability, and this one looks like a joke, but ask any professor after his graduate student graduates whether he could reproduce the results that were just submitted to a journal months before. So repeatability means that a researcher can reliably repeat their own computation. Replicability means that an independent group can take the author's tools, the author's software and hardware, and get the same answer. In other words, the paper was complete enough to describe the full computational workload. And reproducibility means that an independent group can read the paper, write their own code, run it on their own computer, and there's enough information in the paper that that result can be reproduced. So this is an increasingly tough set of standards to earn this badge. And the conferences to which my group submits, like Supercomputing in the US, we try to go for these badges after the paper is accepted by putting the code at GitHub or by giving appendices. Standardization of tools. Here I'll just live with an example. The message passing interface, or MPI, which you can look up at mpiforum.org, back in the 1980s, when parallel computers were coming online, every single vendor had their own way of sending a message from one memory bin to another on a different node. And that meant that codes had to be rewritten when you went from one vendor's machine to another, unlike the computer languages themselves. So this is now a universal standard. I know of 0 exceptions in the high-performance computing industry. Maybe some banks, maybe some military have their own exceptions for security reasons. But this is a hardware-portable, multiple-language communication library. It allows flourishing of open-source applications. It met first in 1992, released its first commonly agreed upon standard in 1994, and is still meeting about every year. It's now up to MPI 5.0. It involved 80 people from 40 organizations spanning everybody who cares about computers, the people who build them, the people who research them, the people that use them, contributed by their organizations, funded by the US government. It's in continual adaptation because as memory systems evolve, there's more things you can do with message passing to make it more efficient. And this is a historical photograph from one of the MPI Forum meetings. We need that in the quantum industry. We need something like the ITRS roadmap, the International Technology Roadmap for Semiconductors, which you can find an article about here. This roadmap took us from about 180 nanometers to today's 3 nanometers, the industry working together, releasing their projections pre-competitively. Of course, they had their own copyrights and trademarks and reserved patents, but it was actually beneficial to training the workforce and allowing manufacturers expecting to use the vendors' chips to know what was coming. And so the predecessor to the ITRS began in 1993 and ran until 2017, and now there's a new one called the IDRS, which was just established. And the quantum industry does not have this. We also don't have discipline-wide benchmark problems. Here's an example from the aerodynamics community showing a standard wing type in 3D, the M6 wing. Everybody who writes an aerodynamics code proves that it gets the right answer on this wing before they go to the full airplane or the full nacelle of a turbine or whatever. This is also becoming more common in data analytics, like the Netflix challenge. It's now being applied in scientific machine learning, but it's not yet established in quantum computing. We need that. We don't have any industry-wide performance benchmarks. The top 500 machines in the world submit their speed on solving a linear system every year, twice a year, to top500.org. That's how I know, for instance, that our supercomputer at KFUPM is number 38 in the world. Then there's the green 500, which is how many gigaflops per watt. Not how many gigaflops, that's on the left, but this is how many gigaflops per watt. So it rewards efficiency. There's a discrete graph algorithm benchmark called the Graph 500. There's the high performance conjugate gradient benchmark. The top one features dense linear algebra, the bottom one features sparse. The top one rewards your CPUs, the bottom one rewards your memory bandwidth. So they're different benchmarks for the same hardware. The Chinese have an HPC AI 500 where they rank on some AI algorithms. And there's another benchmark for geometric multigrid, which seems to have gone a little bit out of fashion at the moment. But these are just examples of common inner kernels that we need in high-performance computing. Also, you know, something like the quantum Fourier transform would be useful to have a benchmark. What do I mean by a virtuous cycle? I mean this circle where science and engineering generate questions, software and hardware generate computations, and out of that comes data, which leads to hypotheses, and this goes around and around. And you know, we need to insert QPUs into this cycle to generate insights that generate questions, technologies that lead to better computations, and data that leads to the archives that inspires the scientists and engineers. We need verticals. What's a vertical? Oil and gas, finance, pharma, aero, auto, et cetera. These are money-making things for HPC industry. And all of them depend on many aspects. They depend on understanding the problem from the physical world, building a mathematical model, discretizing the mathematical model into things that can be done with computer arithmetic, creating a solution algorithm, implementing the algorithm in computer code, and then executing it on hardware. We don't have, you know, this kind of picture of a vertical yet in any quantum. You'll hear people talk about finance and pharma, but all they're doing is solving like one piece of this, like maybe the solution algorithm. We need to get it integrated. Something that really makes conventional supercomputing valuable is the human-computer interaction. Here's my colleague Ibrahim Hotet interacting with the circulation of the Red Sea on a viz wall at KFUPM. His finger motions are picked up, and he can you know, introduce perturbations into the computer model. For instance, trace an oil spill that he puts at a place and sees how the circulation will take it. But what do I mean by physical modeling and performance modeling? This diagram launched a program which is now in its 25th year in the US Department of Energy called Scientific Discovery Through Advanced Computing, whereby many scientists worked on this validation and verification loop, starting from a model to the code, to the prediction, to the comparison, and if there was disagreement, you keep going around this V and V loop until you get the science right. And then once your science is right, are you done? No, you probably have a very inefficient code. That's when you bring in the computer scientists who run through a performance loop and optimize that. And then what pops out after the applications team and the enabling team of math and CS work on a code is a user laboratory, like a telescope, a microscope, a spectrometer, an accelerator. It's a tool for scientific discovery. This is part of the culture of HPC. Hourglass refers to this concept that we have many applications that can run on many different architectures coded once to an application programmer interface. And this derives from the 7-layer internet protocol. Think about the internet. You can order shoes from Amazon, but you can also download a weather report from, you know, the National Bureau of Weather through the same internet browser. There couldn't be, you know, one of they can run on any, you know, hyperscaler farm in the world for any application, but they all have a common World Wide Web internet-based protocol in the middle that enables these things to interoperate. So when I say convergence of the paradigms, I'm referring to the fact that any of these three HPC paradigms help the other when any one improves. So for instance, data analytics provides steering in high-dimensional parameter space to simulations and in-situ processing of data. Machine learning provides replacement of first principles models with learned functions from the data or smart data compression. Simulation provides to analytics physics-based regularization, so you don't just have statistics. You say, does it satisfy the law of conservation of energy? Are all the densities positive? You know, are all the interest rates, you know, within a certain range? You know, whatever your model has, there are some constraints on it coming from simulation. And machine learning provides to analytics detection and classification and imputation of missing data. And simulation provides to learning data that augments real-world data if you trust the simulation because of your V&V, and data analytics can clean those feature vectors for good training. Traditional simulation doesn't learn. You have some inputs, you have some outputs, and what's under there is a black box. If you peel that black box label off in the future, you'll see that there's a simulation analytics learning loop where simulation it uses models to generate data, and learning uses data to generate models in this virtuous loop here. Now, there's 12 elements of HPC that have made it a smashing success. Hybrid systems inherit all this because they're glued into the HPC. All those 12 things come along for the ride once you find the QPU that maximizes some portion of your HPC code. In some sense, quantum computing has the luxury of being born into an economically viable, scientifically exciting, trusted ecosystem. And therefore, it can evolve steadily. It doesn't have to do everything all at once. It can fill in one piece at a time, just as GPU computing did over the past 15 years. Until now, nobody's interested in your code until you have part of it running on GPUs. And both circuit-based and adiabatic-based, like D-Wave, will rapidly take over whatever they can do more efficiently than the other two kinds of processing. We need the motivational manifestos for the stakeholders, and Saudi Arabia has begun to work on that with the World Economic Forum through, for example, the Quantum Economy Landscape Report that came out in December of last year, the efforts including some of the people in this room. And on the left, we have a report that actually I edited for the US Department of Energy back in the early 2000s. 315 people funded by the Department of Energy were asked certain questions about what HPC could do for them if they got a 100-fold improvement in memory and processing power. And then we fashioned that into a set of reports that then liberated money for this now 25-year SIDAC program. So what lessons can we draw from CPU-based HPC? Develop good open source culture so that everybody helps you fix your code. Everybody debugs your code. Everybody adds cool things to your code. Each advance in one area quickly fuels advances in the other areas. And from the GPU-CPU hybrid HPC, we learned that resistance is futile. You cannot promote a code today that doesn't have the GPU part. And in the short distance, the time of all the young people in this room who are studying math, physics, chemistry, computer science, you will not be able to advance until you claim how you're integrating the newly available quantum computing. This is a vision from 2014 from the US Department of Energy called Co-Design for HPC, talking about the integration on one node of many kinds of processors, CPU fat cores with a lot of memory and latency hiding, GPU thin cores with high memory bandwidth but small memory, and off to the side, slow DRAM memory, fast flash memory, 3D stacked memory, integration with the communication network and so forth. My vision to augment this is if we can get quantum out of the cryostat, we will have some close coupling of QPUs with the CPUs and GPUs. And they will share data efficiently and deliver for us. This is a picture of Shaheen. It's an impressive piece of hardware, but what really makes it sing is the data structures, the task graphs, the communication patterns. And I'm wondering myself, will it get a QPU before I retire? I don't know, but I'm hoping that it will. So my summary about the earliest quantum advantage is it will be a hybrid quantum classical computing system. We don't have to wait for a freestanding universal quantum computer. You've already seen several examples at HPC centers around the world with a supercomputer QPU pairing, and places where it's available in the cloud, and places where it can be emulated with quantum algorithms, even though some places don't have quantum hardware. We've seen where that is happening, and now it can happen in the KSA through emulation or perhaps through the graces of Aramco. In terms of when, if you haven't started, you're already behind. Yes, there's no reliable quantum hardware, but there's a lot of interesting algorithms to start thinking about how to integrate. Why? I'm going to leave the use cases, the finance, the pharma, the oil and gas, to other people in this symposium, but my contribution, I hope, my advocacy anyway, I don't have any proof, I've just been observing QPUs from the HPC side, is that there are some clearly marked paths to follow in CPU parallel and GPU-CPU integration that now need the attention of QPUs. So the advice of a legacy digital to young quantum is that history does not exactly repeat itself, but it does rhyme. And if you're interested in that quote, it comes from the American humorist Mark Twain. History doesn't exactly repeat itself, but it often rhymes. And that's where we sit today as we look at the 100th anniversary of quantum mechanics. This article on the left is where Schrödinger's equation was first published. It was derived in 1925, published in 1926. Already in 1927, these 29 world-renowned physicists, 17 of whom went on to win Nobel Prizes, got together in Solvay. I think, if I'm correctly remembering, I think that's in Belgium. I'm not exactly sure. Maybe someone can correct me. But where is it? Yeah, yeah. So there is a Schrödinger who is considered to have put the thing on its math foundations. You can see Einstein behind him, 2 to the left of Einstein. You can see Marie Curie. All these Nobel winners quickly picked up on a new technology, and indeed we have the International Year of Quantum. Here is the logo you're going to be seeing a lot of this year. And I will end with my own ode to quantum. Von Neumann once told a student, don't worry about understanding quantum mechanics, just get used to it. Even I don't understand it, I'm just getting used to it. This is how it works, right? Okay, so this is my poem. We are getting used to you, like von Neumann, so we too. Feynman took a careful look, and since that day, we've all been hooked. In most of life, large size takes all, but your potential's in the small, oh quantum. Entanglement defies belief. Of all your miracles, it is chief. Superposition reigns supreme at once, all values, what a dream. but decoherence complicates. We trust solutions lie in wait, oh quantum. To stay ahead in crypto wars, we are studying Peter Shor. For large-scale search, we'll ask Lev Grover. In square root time, the search is over. To optimize, we have a feeling we can't do better than annealing, oh quantum. Qiskit, Q-sharp, Silk, or Circ, which language will streamline our work? Photonic networks, neutral atoms, trapped ions, quantum dots, tunnel junctions, diamond defects. For devices, we'll take our shots, oh quantum. Science is but half your story. Mystery adds to your glory. Into our thoughts deterministic, you inject a touch artistic. We celebrate the great expanse opened by your world of chance, oh quantum. Watching's fun, but we want more. Thus we're swarming at your door. Older souls may skip this race. Let the younger set the pace. Nations that in you invest anticipate a future blessed, oh quantum. You are not for the faint-hearted, but we are ready to get started. We know we have lots to learn, but bargain on a large return. Early though your hour is, we gather where your power is, oh quantum. And that is exactly, thank you, Shukran. That is exactly what you are doing today, old or young. You're not going to be on the sidelines. You're here thanks to KFUPM to be informed. And I hope that, that this is just the beginning of many collaborative relationships. If you feel left out, if you're not lucky enough to be at KFUPM, you can join our reading group virtually. We're in the middle of a short course by NVIDIA that takes up February, but in March, we'll open up a new chapter. And my colleague, Dr. Samara Siri, Samara, stand up for a moment. She is helping me run this group at KAUST. So she's here to make contacts with you all as well. Thank you, Samara. So let's enter. And thanks for your attention. I don't know if I've gone past my time or not. I see a hand over there. Okay, so the integration, the big computer science problem, how do you have one system that integrates three resources, many jobs that are going to alternate between their need or their opportunity for those resources so they don't stomp on each other. And so, for example, I mean, in some sense, we do this today with parallel computers. We have some jobs that need 1,000 nodes, some jobs that need 100 nodes. The job that needs 100 has to finish before the 1,000 can be allocated. We have sophisticated workload managers like Slurm that are trying to bin pack space and time in an efficient way. When quantum comes, it will greatly complicate that because it wants access to the memory of the other system in real time. So I think the simple thing to do would just be to say, okay, you get the supercomputer between 1 and 1:30, she gets it between 1:30. But that is, of course, way too inefficient. So I'm not sure what the low-hanging fruit is, but I know that, that it's going to be some really smart computer scientist that solves that dynamic optimization problem. And maybe it will be you, because I know it's not going to be me. Yes?
Thank you very much for so detailed stimulation talk and the quality of quantum mechanics.
Thank you.
Really appreciate your efforts. My question is when this quantum computing will be in the hand of a common man or out of the world?
Okay, it's not going to be in your cell phone for a long time. And it's not going to be in your home computer for a long time because you don't have problems that are that big. To get quantum advantage, to be out on that asymptote where a square root or a log becomes important, you have a very powerful classical computing to beat right now. The NVIDIA and the AMD and the Intel GPUs are just incredible. And that's, you know, in some sense, the goal of quantum advantage keeps getting further out with every improvement of classical computing. But classical computing is going to hit an energy barrier. As Sam Altman says, we could use an infinite, almost an unexhaustible amount of knowledge coming from querying LLMs, which have ingested the entire internet. But we don't have enough energy for every person on Earth to be able to make those queries, to decide, you know, whether it's going to rain tomorrow or when the car should be repaired or what's missing from the refrigerator for the next. I mean, those kind of things that could help us, they're energy limited. So there will be some quantum back end to some of these major clouds maybe that will pay first. And we won't see it, except we'll have a smaller bill for using, you know, those systems. But the scientists will see it. The people who are doing materials discovery, like Ahmed talked about, you know, where in the periodic table can I find the 3 elements that will give me an alloy with this density, thermal conductivity, stress? That kind of optimization problem is probably going to be one of the earliest exciting uses of quantum. I think, you know, the killer app, I don't know when that will come. It's projected to be about 1,000 reliable qubits out before we can all read each other's emails, you know, that are just RSA encrypted. But an early application will, of course, be quantum encryption. You know, we'll want to develop algorithms with quantum key cryptography that cannot be broken by other quantum computers. So that will be, that might be the first thing. You asked common man. That might be the first thing, that when you send a file behind the scenes somewhere, there'll be a unique key generated that will be, you know, entangled some way and yeah. But, you know, we're talking about computing. Quantum sensing and quantum communication are already widespread. You can do quantum encryption over optical fiber for, I think, something like 100 kilometers now. So Singapore, you know, can cover the whole country, you know, with something like that. And they are investing. And you know, our infrastructure will be replaced with some of these already mature technologies long before we replace, you know, algorithms with these alternatives. These papers are hard to read. I'm a mathematician, and I find these papers very hard to read. You know, they're not going to be something that you're going to have a homework assignment in 6th grade, you know, develop the quantum Fourier transform. Yeah.
There are many pathways people are trying in the world. So, I mean, they are using, optical also method and this LC circuit and all this. What is the best method you think will be achievable at room temperature?
Okay, so you're asking me which quantum qubit device is likely to be the winner of the arms race. I don't know. I mean, you know, we've heard 3 speakers this morning praising the Josephson junction as something that's easy to manufacture and control because it's a little more macro than ions or atoms or photons. Yeah, that one uses a lot of energy. That's a cryostat. I'm rooting for, I mean, I shouldn't pick favorites because it will probably be something I've never heard of. But, I mean, it would be great if it was photonics because then we can all use it at room temperature. Yeah. But, you know, each technology has pros and cons. I mean, some of them are hard to entangle, some of them decohere quickly. We don't have the perfect qubit. It was in, you know, the mind of some mathematicians using quantum mechanics, but it's not yet been realized in a manufacturable, reproducible way. That's why the race is on.
Thank you very much.
Pleasure. Yeah. Ahmed, yes, thank you for preparing my talk so well.
Thank you very much for the insightful talks and presentation. Actually, I have a question and one comment, but let's start with the question. The question is for someone like you who has been in this region for a long time, and as you know, I'm not talking about Saudi Arabia, I'm talking about the Arab region. We wanted to invest our efforts, especially with the youth, for the advanced technologies, especially in quantum. And there is a lot of debate about whether we can invest it in software, hardware, algorithms, you know what I mean?
Mm-hmm.
So based on your research background and based on your stay and connection with us, so where do you think that we as nations or universities, businesses, government needs to invest more? Is it the hardware, software, striking a balance? You know how is the competition or the landscape worldwide?
Yeah. The good news about quantum is that you can access it in its fundamental difference at a very small scale. I mean, you can emulate just like, say, 4 qubits on a laptop and start to see how these circuits are built and, sort of watch, the bits, the qubits flip or, whatever. I mean, so there is a low-hanging educational opportunity. My impression of regional youth is that they're much more interested in doing the leapfrog. In a lot of other mature countries, the kids don't have the same motivation to, let's have our country leapfrog. They're just sort of riding along. They're not as drawn to a brand new technology like quantum as I have detected here. But in terms of investment, I would not start by buying a lot of today's systems to see which one is best, because they're all still fairly expensive because they're not being stamped out in a mass market way, and we don't know which one will scale or be reliable the longest. I would concentrate on an emulator and some high-level language. I'm not advocating NVIDIA, but they have one example that backends to many, including yours. But Qiskit is a good one from IBM. There are many that are back-ending to many different systems these days. And so if you develop your code using one of their languages, then you're ready for whichever qubit integration comes along. So there is a chance to get started at a very low-hanging end. We should, I think during the year of quantum, we should try to attract many people to, what is this thing that the UN has declared, and, have workshops, have a national quantum day like we will in Riyadh on April 13th, I think it is, and so forth. So that's a rambling answer to your first question. Now you had a comment.
Yeah, my comment is about cryogen, because maybe there is a misunderstanding.
Okay.
In the technology, there are many innovations in hardware and software. So, for example, there is an increase in qubits. There is an advancement in control systems, in microwave, and also in cryogen. So
true.
There is a lot of advancement.
True.
And people think that it will consume a lot of energy. So in System 2, for example, in IBM, the consumption is 60 up to 100 kilowatts, which is a fraction of
yeah, that's just right. It's just the same amount as a GPU rack. That's right.
So
yeah.
That's
Okay. Okay. Well, that's actually a very valuable number. I admit, I freely confess, I've been scared by the cryostat. I mean, 4 Kelvin. That's cold. Yeah. Okay. Thank you. So.
I think we should close the phone for questions. We do not go over time. Unfortunately, we have to close it here. So I'd like to thank Professor Keys for his presentation with a small token. So please welcome Dr. Keys once more.
I'm very happy to be here. It's a real pleasure to be here. So before going through the content of the talk, I will start by introducing Eviden Athos, who we are and what we do. So at Eviden, previously Atos, we are doing a quantum emulator. Atos is leading HPC in Europe, and we are delivering HPC system all around the world also, sorry. We, thanks to this knowledge in HPC, we have built a quantum emulator. So it's a classical HPC system with a software stack on top, allowing to emulate quantum circuits. And we are very honored to have delivered the Captiva machine. So this is the name of our appliance to KFUPM. So we are pioneer in quantum emulation, since 2016, and we are a leader in HPC quantum hybridization. So it will make an echo of the question of the previous talk, because we are involved in many hybrid HPC quantum integration in Europe. In Germany, for example, we have installed a Captiva machine in a HPC center, and we have developed specific tools in order to be able to schedule hybrid HPC quantum jobs in HPC systems. Also, we developed QPragma, which is some HPC stack for HPC developer to be able to integrate some quantum codes in their HPC code. Okay.
It's better now? Oh yeah. Okay, thank you. So we have many quantum patents because we have a huge R&D. We are based in France. So just an overview of our stack. So using Captiva machine, our appliance, you can emulate quantum circuits from the three main quantum paradigm, from gate-based, annealing, and analog. So we can do full state vector simulation, but we have some much more specific emulator like MPS, and we can do noisy simulation, so you can integrate the noise of specific QPU depending on the hardware and so on. We can do annealing, simulated quantum annealing, so we can simulate what D-wave do, for example. And we can emulate the analog paradigm also, so the schedule of an Hamiltonian. One important part is the optimization of quantum circuits, so that to minimize the number of gates, make it compliant to a specific target, a QPU target. And we have either on-premise or as a service. We also we have installed a Spark QPU, so the IQM quantum computers in our premises in France. So we have the ability to install quantum computers. And from Captiva, you can send some job also on remote quantum computers. And of course, we can interface with other language. So now I will speak more in details about some application we worked on at Evident, because as I'm a quantum computing consultant, so my job is when a customer comes to us with a specific use case to give a quantum formulation of its problem, and I will talk about some use cases we either worked with some customer or we have developed at Evident, and some other interesting application. So first, we have mentioned that all along the first talk this morning. Quantum computing itself is a paradox, because we want to make some a computation with a quantum system which is isolated from anything the environment, because the quantum system is subject to any perturbation like the light, some photons, the vibration of sounds, and also high energy particles. But on the other hand, we have to make some operation to make the computation. So we need to apply some quantum gates and to measure. So we need to open a channel on the quantum system, which introduce some noise and so on. So here is the paradox, and this paradox is observable because when you are in front of a real quantum computer, you make some quantum operation. You can see the temperature of the QPU, which increase a little bit. So your operation are acting, perturbating the quantum system. But you may have noticed that the subject of the talk is the paradox, but practicable applications. So what can we do actually using either our simulator or our QPU? So what I won't speak about, so yeah, I will not speak about Shor's algorithm because it's not practicable. We have seen that it requires too many quantum gates. So this is not a 2 days application, practicable application. Same thing for Grover's algorithms. We cannot run it actually on QPUs. But what can we expect in today's application? So one application, quantum machine learning, very interesting because we can think about the fact that machine learning models are kind of resilient to noise by default because datasets are noisy. So we can think that if a quantum machine learning model is resilient to noise, it could be the same with a QPU. Quantum-inspired approach. Quantum-inspired is how we can take a classical machine to solve, to run on to run quantum algorithm. So this is where quantum emulation are used to, and quantum simulation is simulating a quantum system with another quantum system. So first application I would like to highlight here is a quantum-inspired algorithm for anomaly detection. So this is one application I worked on, I have developed. There is a reference here. So basically the idea is that in machine learning, in classical machine learning models, to detect some anomalies, what we will try to do is to find the point in the data set that are most distant from the center of the data set. Another common method is based on the density. So given a point in the data set, computing the density over the other neighboring data point, and the lower the density is, the most probable anomaly you are. And the idea in this the quantum version of these use cases, this use case is to combine both methods. So we would like to, at the same time, maximize to select data points that maximize the distance with the center, and which maximize also the density, minimize the density, sorry, of neighbors. And this formulation of this use case has been run on a quantum emulator like our, and gives some good result because we have benchmarked against some different kind of data set. So the NIST dataset with the unwritten digits and the credit card fraud detection. So here, this one is quantum inspired because it cannot run actually on real QPU because of hardware constraint of actual QPUs. So we can only actually run it on simulators, and this is why it's a quantum inspired algorithm. Another application, we have worked with one of our customers. I cannot name it, but name it. Sorry. The goal here is to minimize the emission of carbon dioxide during the transportation of pieces. So big industry like aeronautics or automobile. So some industry who are building some plane, for example, we can imagine that there are many pieces that are manufactured in specific sites, and each pieces must be transported to another site to be mounted. So there is this kind of tree architecture of pieces to be manufactured and transported. And the idea, the goal is to allocate a site of manufacturing of some pieces, so that we want at the end of the day to minimize the carbon emission when you will transport all pieces of your plane or your car. So for this project, we have developed a quantum algorithm to solve it for gate-based, analog, annealing, and we have tried to find the best formulation of the problem. And using simulated annealing, we have been able to reach, to be able to find the best solution. So the minimum energy of the way we have formulated the problem, and we have been able to reach the lowest cost, the cost in terms of carbon dioxide emission, in less time than the classical way they are doing actually. Finally, this is a much more prospective application of a use case. This is a very important topic actually. So this is how we can capture CO2 in pre-combustion, because in energy plant we want to generate energy from fuel, and the idea here is to capture the CO2 before the combustion. And to do so, the physical absorption is used, and the idea is we use a solvent that will capture the CO2 in the syngas, and the efficiency of the physical absorption really depends on the solvent. And the idea is using a quantum application, a quantum algorithm to optimize, to find the right solvent, which will allow a good selectivity. So how I will select either CO2 from hydrogen, and this process applies at high temperature. So we will mount a solvent that will be more efficient at specific temperature. So to do so, we imagine that a quantum algorithm will be a good candidate to find a new solvent that will be more efficient to capture CO2. And how to do? So, as we mentioned previously, it sounds like natural to use a quantum system to simulate another quantum system. So, like what is done on an analog quantum computer, we can simulate some molecules, for example, using atoms. And given a solvent target, so a solvent that is actually used in power plants, we have some candidates. We want to find some candidates that will capture CO2 effectively. And for both, I will create a graph with physical chemistry parameters, embedding this physical chemistry parameters. And we will let the system evaluate in the time, and we will have a kind of quantum footprint of both systems. And at the end, we will be able to compare the distribution of the states during the time of these quantum systems. So this is a way to have, to simulate quantum molecules and expect that a similar molecule will act in the same way. So we can try to predict like solubility, for example, in this case, the solubility, but in other cases, it could be toxicity and so on. And once again, this kind of quantum algorithm can be simulated on the Captiva machine effectively. So what we can keep in mind for this talk is that current quantum emulators can overcome quantum hardware limitation of current quantum QPUs. If we select the right use case and we formulate it in a good way, we can expect to achieve a better accuracy due to the quantum formulation of the problem, but using a classical hardware. And quantum computing may help in today's challenge. Yeah. Thank you.
Let's welcome the last speaker for today, Ms. Rawan from Pascal, presenting applications of quantum computing.
Good afternoon, everyone. Well, most of you are very familiar. I'm not sure if I should introduce myself, but anyways, my name is Ron. I work for Pascal. I work as a technical business developer, so I try to do like partially business and partially tech stuff. So for today, I'm going to talk a bit about quantum computing industrial applications in quantum computing, but I'll be more focused on neutral atoms technology because that's what we do at Pascal. So first of all, I'm going to start a bit with an intro about Pascal, the company, what we're doing in Saudi and stuff, and then I'm going to discuss a few applications. So what is Pascal? So Pascal is a French scale-up, I'd say. It's recently founded, but we've grown so much in the past few years. So we're almost 300 employees now. And as you can see, those are our co-founders, which one of them is Ellen Aspect, Nobel Prize winner in physics for 2022. As you can see, of course, our HQ is in Paris, but we do have international presence in Europe, North America, Middle East, and Asia. Okay, moving forward to our global presence. I'm so proud of this. So as you can see, those are our clients and partners across the globe. And you can see we have from North America all the way to Japan. Of course, most of our presence is in Europe because it makes more sense. It's closer to our HQ. And then you can see the areas in orange versus the areas in black. So the areas in black are our partners and clients that have remote access to our quantum processing unit. And the areas in orange are the areas where we have either installed or planning to install a quantum processing unit, which one of those areas or one of those countries is, of course, Saudi Arabia. So for those who don't know, we have signed an agreement with Saudi Aramco about May last year to, of course, it's an all-inclusive agreement related to quantum computing. There's more for it, but maybe the most fascinating aspect of that agreement is that we are delivering the first quantum processing unit or quantum computer to Saudi Arabia. That is planned to be delivered mid this year and hopefully commissioned by the end of this year. Okay, so Pascal in Saudi. Well, of course, following the agreement, actually it didn't start from the agreement. It started a little bit earlier when, Wa'ad Ventures, yes, they're here. So it started a little bit earlier, I think in early 2023, if I'm not mistaken with the dates. We've had our Series B, at which Wa'ad Ventures, Aramco venture arm, has invested in Pascal. And then Wa'ad have, of course, promoted and supported in Pascal's localization. Moving forward to then, having the agreement with Saudi Aramco, which is also here, so one of our partners as well. Of course, not also forgetting, when we also did our localization, there is also KFUPM that we have participated in one of the startup competitions that was organized by KFUPM, and they were very generous to provide us with so much support in localizing. And of course, we've signed an MOU with KFUPM about October last year, so very recent, but I'm so happy with this, to, of course, train local workforce and also hopefully do a lot more R&D. We also had a partnership with Context, which will be our main cloud provider. So if you know, just to give you a little bit of how our infrastructure is going to be, so we're going to deploy a quantum processing unit in Saudi. Location is not confirmed, because I know many of you are going to ask. And then that computer is going to be accessible via cloud to our partners and clients in the region. And that cloud access is going to be via Context, which is a joint venture between Aramco and Google Cloud, for those who don't know. So we're also very happy with this. Of course, KFUPM is our ecosystem partner. We've also signed an agreement with NITA. We've announced that agreement in LEAP to also train honestly, it's a co-developed program. For now, our students are Saudi Aramco employees, but I think it can be extended to way more. So for those who are interested in training programs that are co-developed by Pascal and Nita, please go ahead and contact them to see their offerings. And we're also very happy to also announce, well, I have so many announcements, this presentation. I didn't realize it was this much until I just started talking about it, so please bear with me. And then with Garage, we're also very happy to have participated in Riyadh Royal Commission Digital District Program, which has been launched, and we've taken part in it. And our office is currently at the Garage. So this is just a glance of how is our presence in Saudi looks like. Okay, that's a bit too straightforward. So moving forward to the hardware. So I'm not sure if you guys are familiar, but just a little bit of how neutral atom quantum computers work. So as you can see, we have a laser source, of course, and then that laser source is shined onto this circle. This circle is a vacuum chamber. Inside this vacuum chamber, there is a register of atoms. Okay? So how does those atoms look like? It's a 2D lattice for now. It's a 2D lattice. It looks like this. And then how do we allocate the atoms? You know, how do we change its place in the lattice? Using optical tweezers. So we basically leverage optical tweezers technology to change the locations of atoms, and then we place those atoms in whatever location we'd like in the lattice. So, yeah. So what is the significance of using neutral atoms quantum computers? There are two main features, I'd say, that are most dominant in this technology. First feature is unique scalability potential. So they're very scalable because they are neutral. They exhibit no charge. And it's basically very easy to scale them without, you know, having those repulsive attraction forces that would disturb the system. And the second one is high flexibility potential. So as you can see, we can basically allocate the atoms in whatever topology we'd like. That can also be 3D. Now, I'm just going to elaborate a bit on the 3D point. We can place them in 3D, yes. This is something we've already published. Now, the thing that I need to clarify is that those are not atoms. So there is a difference between placing atoms. Those are not qubits, sorry. There is a difference in placing atoms in whatever configuration you want, and there's a difference between placing qubits in whatever configuration you want. Now, those are atoms, yes, but they're not qubits, so we don't compute with those. Do we want to compute with those? Yes, but can we? Not yet. So you might see, you might see this configuration as 3D, and then you think, yeah, maybe I can compute with those, but actually not yet. Hopefully, but not yet. So what can we compute with? For now, we're computing with 2D configurations. Okay. So for those who don't know, Pascal is actually a spin-off of a research lab at France. And we have successfully industrialized or commercialized our lab setup. And by commercializing, I mean we can now run it at room temperature. We have off-the-shelf components. And also, like you can see, the low energy consumption at less than 10 kilowatts. Sorry, I'm just going to stop a bit. So how does our offering looks like? So of course we do build our own hardware. So we manufacture the quantum processing unit. We put all the atoms and lasers and mirrors, the whole thing we do at in France. We also have just opened our second factory in Canada as well. So so yeah, what are our offerings through this hardware? So we can allow access via cloud, and we also have our own coding platforms, which is Pulsar. I'm going to emphasize a bit, and then we can also develop practical applications compatible with our hardware, and then we can always provide support like R&D support, tech support, etc. So you can see like we're a full stack quantum computing company. We're not really restricted to any aspect of quantum computers. We quite literally do everything, yes. So you can see a mixture of hardware and software, we all do, and those are our partners and customers in each area that serves quantum computing. You can see like end users, cloud access, application development, and programming environment. One of which is Atos, which was just here. Okay, let's go moving forward to use cases, and it's just like applications. What can we do? What we're doing, and our portfolio. So as you can see here, those are our customers, the locations of our customers, and the use cases that we're doing with each of those. So you can see there's quite a wide range of use cases that you can do in many industries. Because I often get this question that, okay, whom are your end clients? Like, what industries do you operate in? And like, I always tell them we can operate in literally every industry possible. We don't have a specific industry, but it just depends on the problem description. So so the thing is, we don't like only serve oil and gas as an industry. No, we serve all industries, but the thing that is in common of all those industries is that they have a problem description very compatible with our quantum processing unit. I'm not sure if the difference is a bit clear, but basically this is how we serve our clients, or like this is the industry that we serve, the one that has a compatible problem description. Okay, so algorithm overview. Of course, we're focusing on 4 areas or 4 directions. Whenever we're looking at problems to develop use cases for, or when we're looking at problems where we would like to develop an industrial solution. First, quantum evolution kernel. Quantum evolution kernel is an algorithm developed by Pascal, and the idea for quantum evolution kernel is your ability to distinguish between 2 graphs. So basically you have graph A and graph B, and then you're trying to very well tell the difference between A and B, or very well be able to say this is not similar to this. Well, this seems like an easy task, but apparently when it gets very complex, it's not that easy. And then, of course, differentiable quantum circuits. I don't like to talk about this a lot because it requires digital quantum computing, and we don't have this yet, unfortunately. So I always like to focus more on quantum evolution kernel, optimization, and quantum generative modeling. So differentiable quantum circuits is also an algorithm developed by Pascal that allows you to solve differential equations, which governs a lot of problems in the industry, of course. Okay. And then quantum generative modeling allows you to very well generate any set of data, or like any randomized set of data. So you want a bunch of data, but you also want it to be very random, right? I think quantum systems is the perfect tool to do that, because when you're using quantum mechanics, quantum are naturally probabilistic, so they will give you like the most random outputs for that. And then finally, optimization. I think this is very common for all of you. We also do optimization problems when, of course, they respect our hardware constraints. One last thing is like quantum machine learning. I think I'm just going to mention that like really fast because often people think like quantum machine learning is like something that's totally new. It's not totally new. It's literally, quite literally, basically the same machine learning that you already have, that you're already working with, except that you have a quantum layer to enhance your quantum machine learning model. This quantum layer is usually, from what I've seen, it's an emerging field, so maybe there are lots of things that I still haven't looked at. But from what I've seen is like at the pre-processing unit, you're trying to basically maybe extract more accurate features or get more or train more randomized data based on quantum computing. So yeah, this is what quantum machine learning is, and we do a lot with it, honestly. This is also, maybe, I think I do have a lot of background before going on to the use cases because I just want to make sure that when I'm talking about the use case, like it's very clear that what we're leveraging, what we're not leveraging, what we're focusing on, and what we're trying to ignore. So as you can see, digital approach and analog approach. The digital approach is the most common, where you basically apply gates to each qubit, and then you get an outcome. However, what we're focusing on more at Pascal and what actually shows neutral atoms potential is analog approach. In analog approach, you are shining a laser, physically, you're shining a laser on the entire ensemble of atoms. And if we look at it as a gate, this is how it looks like. So there's just one single gate that is applied on the whole thing. Like as you can see here, Hamiltonian, like this is the description of Hamiltonian. And as you can see here, you're shining lasers on like one singular atoms instead of like the whole thing. Okay, great. Moving on to use cases. So predicting toxicity. So here, when we're talking about molecules, well, apparently, we would like to very well understand the molecules, the difference between them, their structure, etc. And apparently, this is a very challenging problem. So why is it a very challenging problem? Because we cannot predict properties of those molecules very efficiently. And how is it like? So, for example, with a classical computer, it's actually hard to tell the difference between this graph and this graph. And why is that? Because they acquire the same number of vertices. So you see 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. So like literally same number of vertices. And they also have the same number of edges. Like also, if you count the edges, they're the same. So classical computers would think that these two graphs are identical. Or if it's like in molecule setup, they would think that those two molecules are identical. However, because we're using quantum computers that are naturally interacting with each other, we can leverage quantum evolution kernel, the algorithm that I just went through, to actually be able to tell the difference between one molecule and the other. And if you can see here, like if you have this molecule, you can then, map it. This is not very accurate, by the way. It's just to emphasize the ability of mapping a molecule structure into an atom structure in the QPU. This is actually very doable in the QPU. Of course, these are some results. So you can see that, honestly, the end result is that the QPU performance matches with the current classical approach. So it's not way better. However, it is a simpler model. Okay, now combinatorial optimization. So yeah, I hope the area where we're telling the difference between two graphs is done, because this is one application for it. I'm not going to talk a lot more because it applies to a lot similar applications. So if you have basically two networks or two graphs, because we also apply it in banks, for example. So if you have two networks, so in banks, they describe their chain of operations in networks. And then if one network is identical to the optimal network, this is, the approach as well. However, if there is a fraud or an issue with the other network, and then you compare it with the optimal network, you're going to notice that there is actually a problem in the network that you're using. I'm not sure if it's clear, but it's pretty much the same idea as by comparing to the optimal model or to the best model. You can actually tell if your model is performing correctly or not. And this is also like very quickly another application of quantum evolution kernel. So let's go to combinatorial optimization, which is, I think, like the most useful application. It's not the most useful, actually. Simulation is the most useful, in my own humble opinion. But yeah. What can you do with combinatorial optimization? You can do network design. You can do supply chain. You can do scheduling, resource allocation, and portfolio optimization as well. Now, what I'm going to discuss right now is one of the most promising use cases that we've worked on, and it's basically allocating frequencies to 5G network distribution across Paris. Now, why is this very helpful? Is that because in Paris, it's a very condensed city, and then you want to make sure that no nearby antennas. I think I have it in the next slide. Yeah. So you wanna make sure that no nearby antennas have the same frequency. And that's, of course, a very hard task because those atoms or those antennas are basically very close to each other because they're like very dense, right? And how we're describing the antenna placement is by basically representing each antenna as a node. So you can see here. Each atom represents an antenna, yes. And each frequency is a color, because here we're trying to propose a graph coloring problem, but I'm not going to go into that. So as you can see here, we literally place the atoms. By the way, this is how our register looks like when you apply it on our coding platform. And then you're basically placing the antennas, you're basically placing the atoms in the same setup as the antennas. So the antennas has to be here in Paris, like that's realistically, and that's in our QPU. So what are the outcomes for doing so? Is that you have little runtime, and then you also have used less frequencies to allocate, because subscribing for a frequency is quite expensive for those industries. Okay, maybe I'm just going to discuss a bit, because also in the next slide I'm going to discuss a bit how we do it. Now, what is the constraint that we have? Two neighboring antennas cannot have the same frequencies, right? And then we also know that in neutral atom quantum hardware, two atoms cannot be excited at the same time. And the reason why two atoms cannot be excited at the same time is because this atom is going to be really excited, like very, very far, and then it will create some sort of dipole interactions with the neighboring atom. And that's why you cannot really excite an electron like too far. And then in the neighboring atom, you're going to excite the electron too far. They're just going to repel each other. And that's why you cannot excite them both. If one is excited, the other one is not. And in computational form, if one is 0, the other one is 1. And in terms of frequencies, if one is frequency A, the other should be frequency B. And that's exactly what we want, right? And that's why we are basically allocating those antennas exactly similar to, we're allocating those atoms exactly similar to the antennas configuration. And then our frequency is, and then we first solve it as a, I don't want to go into too much details, but we first solve it as a maximum independent set, and then we solve it as a graph coloring problem, at which the color is basically the frequency. Yeah, there's a bit more details here, but I think I'm just going to skip it because I think it's too much details. Is that correct? Yeah. But I think the description I just emphasized is quite good enough. So as you can see here, I'm so sorry, but I have to. So as you can see here, you have like PCI. PCI would be like the frequency. So you have this frequency and this frequency. And then those two yellow frequencies should not be the same. They should be different. And that's why we're taking this frequency into this frequency. And if you can imagine it classically, what you're going to do, you're going to be at this phase where these two cells have the same frequency. And then you're going to say, okay, no, should I put it here? Or should I put this one here? Like, which one? Should I take this one to here? Or should I take this one to here? So just imagine if you're trying to do this classically, how much time it's going to take. Like, for each antenna, you're doing this manually. And that's why our hardware is really well suited for such kind of problems, because it naturally will not give the same state for two neighboring atoms. Okay, it's the same thing here. All the rules and everything, and that's how Rydberg dynamics is very well suited. So if, for example, we have this antenna placement, what we do inside the register is basically place them the same, and then you can see, if they're within radius, they're going to have interference like this. So 2 and 3 will not have the same state, and therefore 2 and 3 antennas will not have the same frequency. Okay, now moving forward to simulations, which what I think is like the most promising. So in condensed matter physics. Okay, Aslan, this is the last slide. So in condensed matter physics, you can see that there is like Ising model, at which the Ising model is basically a lattice of electrons, at which each electron can exhibit in a spin up, spin down, and then they have interactions, right? And this is a very complex problem when done classically. And what we did here, one of our co-founders, Antoine, he published this paper at which he is simulating Ising model using our 2D Rydberg atoms. Of course, there's a lot more in material science or condensed matter physics that can be simulated using our hardware. So you can see magnetic materials like Ising model, and then electronic materials like Fermi-Hubbard model, and then amorphous solids as well. And those are our partners for each of the type of materials, and all the industries at which this can be applied. The model can be applied. Well, lastly, I forgot about this. Lastly, we have Pascal community. I invite you all to join, please. And we also have a webinar that will introduce the community that will be held in February 25th, which is like next week. Okay. So yeah, I invite you all to be here, and thank you so much for listening.
Yeah. Thank you, Ms. Saraki, for the presentation. Oh, one more question.
Okay, thank you everyone for this nice talk. I think you are a good seller for your company But since we are coming from physics, I would like to ask you, is your quantum computing or whatever you call it, is it a black box? You don't want to disclose whatever is inside? How many atoms? How do you manipulate them? Or for each problem, you take the tweezers and you change the position of these atoms? And or like D-Wave, they never mentioned whatever they have in there, like quantum computing.
I think, what's inside the quantum processing unit is very clear. I just emphasized a bit. So it's actually not very complicated. So you have atoms, and then you are changing the place of the atoms. And yes, the places of the atoms is changed based on the problem. So every time we're running an experiment, we change the location of the atoms.
Any more questions?
Our currently available quantum computer in the cloud is 100 qubit, but the one we're delivering to in Saudi is going to be 200 qubits.
Yes, thank you, Mr. Raqib, for presenting.
Neutral atoms. Neutral atoms. So generally, generally it's run in room temperature. Well, as you can see in the industrialization, and that's like one aspect of our commercialization to the technology. However, inside the vacuum chamber, it is cryogenic. But outside, anywhere outside is not cryogenic. So we just reduce the temperature only inside the vacuum chamber. Anywhere else in the hardware is not cryogenic, and that's why it's low energy consumption. Yes, inside the vacuum chamber only. Like it's not a very big chamber. I think it's like this. Yeah, we can take this offline.
Yes. Let's thank Ms. Raqib for her presentation. I'd like to announce we will have a 10-minute break right before we start off the workshop for today. I highly recommend that everybody attends. It's important for the symposium. Thank you.
Test mic. Bismillah ar-Rahman ar-Rahim. Test. بسم الله الرحمن الرحيم. تيست مايك.
السلام عليكم ورحمة الله.
first.
World Economic Forum's C4IR network. The network focuses on adoption of emerging technologies specifically from the public policy aspect. So this workshop is hosted as part of our flagship project, the Quantum project. The Quantum project started in 2024, and for the year 2025, it's a flagship project. In 2024, we hosted celebration for the World Quantum Day, and we published a landscape report that Professor David mentioned earlier. So we'll start with the first panel on workforce development. The second one will be on quantum infrastructure and supply chain. I have with me Professor Matteo and Professor Jacob Dunningham and Engineer Rawan Iraqi. So the goal of our project is to develop a roadmap for a quantum economy, and obviously the first part and probably the most important part is the workforce. So to begin, I want to ask Rawan. So obviously you started. You went from undergrad in physics and you did your master's in quantum computing, and then later a master's in applied physics at KFUPM. So from your translation from academia to industry, what were the most critical skills that you had to develop?
Talking to people. I think that was one of my main struggles, especially like being in research. I'd say I was mostly like working by myself, reading by myself, exploring by myself, and then research is a bit like self-motivated kind of work. You of course you do engage with students, etc., but that's not really the core of your studies. And then of course moving to academia, and then I have to talk to this amount of people, make sure I have a good personality, good spirit as well. I really had to work on those skills in my first few months in the job. Also given my position, so I didn't only work in the industry and a scientific role, so I didn't go from academia into then an R&D in a corporate. No, I went from academia into a commercial role in corporate, and I think that was a very difficult transition. But I would say do work a lot on your soft skills. It's also better if you start working on it early on if you're willing to transition into corporate. Even if you're doing R&D in corporate, you should also have those soft skills for sure.
General question for the whole panel. What kind of industry partnerships that you think will help develop, transition the workforce from classical workforce to quantum workforce? You want to start, Matteo, as an entrepreneur?
Sure. So yeah, my name was Matteo Mariantoni. I know it's complicated to pronounce it. So yeah, I think that's a good question. So let me answer with an example. So in Canada, in the past couple of years, we have developed a workshop together with a company called CMC. This is not a startup company, but what I'm about to say is applicable both to startup companies and more established companies, I guess. And so this workshop, which is called the Building Your Own Superconducting Quantum Circuit, it's a one-week workshop, which happens annually, during which a number of people, for example, some of my students have been teaching in this workshop, so professionals, both from academia and from industry, describe, for example, explain, give tutorials on how to design and fabricate superconducting devices, so that, and the target audience of this workshop are, for example, grad students working on theory, who are actually interested in eventually building an experiment, but they don't have access to any experimental facility. So they don't have access to a clean room facility, and they don't have access to a lab where they can actually perform experiments. But they are interested in quantum technologies, and they want to implement, they want to realize an experiment. Okay, so but they don't have access to any of these facilities. And so what we do in this workshop, we teach them how to design a device, okay, and how to simulate it. How to, from an idea of a Hamiltonian, actually build an actual circuit that works, and then eventually, following certain predefined design rules, we end up fabricating these devices for example, in our clean room facility in Waterloo, we ship back these devices to the designer within a few months time frame, and then depending whether these people have access to their own measurement facility, they can measure the device that they were not able to fabricate on their own. They measure it in their own facility, or we provide ourselves and the equipment, somehow the lab where to measure these devices. So in this sense, this collaboration was very fruitful because, again, it was a collaboration which started with the company, and yeah, comprises people from both the academic world and the industry partners. And I think it was very well, it resonated very well with the community. We had lots of participants, and it really helped somehow boost quantum technologies. And as an example, a smaller example of that, so a sort of miniature nano version of that 1 week workshop will happen this afternoon with a company I'm involved with, which is Red Bull Quantum, in fact, which was also mentioned earlier today here. So they will be hosting a workshop similar to that this afternoon here at KFUPM. So yeah, so in that sense, I think these kind of collaborations can definitely help.
Professor Jacob, I have a question about sensing, since you're an expert on sensing. Are there like programs, do you think, programs or certification that would, like for your average like electrical sensing engineer right now working in industry, would need to start working using quantum sensors?
Yeah, I think the training that goes into people for quantum sensing actually is very similar to the sort of training we'd want to offer for people in any quantum technology. And some of the things we do, similar to what happens at Waterloo actually, is that we engage with industry a lot and try and provide the training that they need. I know quantum companies like Pascal we here do in-house training, and that's fantastic. And so we find that a lot of the companies we end up engaging with are people who are not overtly doing quantum. They're things like financial institutions, and they want their employees to get an overview of quantum and make sure that their business is quantum ready and that they can understand the risks and the opportunities that lie ahead of them. So we work closely with those companies. We talk to them. We often put on bespoke training for them. Along with that, actually, we've recently launched an online master's, which has been really successful. We've got about 100 students in our first cohort. They're all over the world. The nature of it makes it very flexible. So we find that we get a lot of people who are working in quantum industries already, and they can do it part-time, structure it around their work. It doesn't matter what time zone they live in. And each of these individual modules can be taken independently. You don't have to take the same master's. So we're finding companies are now coming to us and, for example, saying we want our workforce to be trained in quantum sensing. They can get a very technical course on that, or they can come along and say, well, we want to learn about, you know, something to do with entrepreneurship and quantum, and we can do that as well. So I think these are great opportunities. Just one final thing. I think it's really helpful to have jointly funded PhD positions, so industry and academia working together, because I think the students gain a lot from that. And I also think the businesses too. They learn a lot about the technical side of things. So I think that package of things has been really successful for us.
Thank you for your answer. You already moved into the question I wanted to ask, which was about like educational programs. You already mentioned the masters you have, I assume, at the University of Sussex. From your point of view, Matteo or Rowan, about like specific programs in quantum technologies, how important are they, and how can we optimize them to help develop future workforce? Do you want to start?
Well, as Jacob said, obviously, I mean, developing locally a program which you know, forms the next generation of scientists working on quantum technology is obviously very important. So, as an example, in Waterloo, we have a very extensive graduate program, and which is working very well. And so I think I would strongly encourage any institution to locally develop, you know, their own program, particularly, well, when it comes to theory, I think having a sort of online master or something like this, it works really well. But when it comes to experiments, you want to have some hands-on training as well. And so, for example, if you want to, you know, learn how to fabricate superconducting circuits in a clean room facility, you cannot do that online, of course, and you cannot do it within a few months. So you really want a couple of years time to have a hands-on training. And so, yeah, so for us, that's experimentalist, that's it's really important to have this kind of local graduate program that helps, create these professionals that eventually can, in the beginning they will be just grad students, but then eventually they can transition into other roles in companies, as engineers.
Sorry, just to follow up, do you think there's a room for undergraduate programs in quantum tech specifically?
I think for sure, obviously, there is a room for undergraduate programs, even though personally, when it comes to undergrad programs, I would focus more on the basics. And so in our experience in Waterloo, the undergrad program in physics, which comprises, all the core courses on quantum physics, quantum mechanics, and all that, suffices at that stage. So we have a few. So what we are doing actually to make to answer your question, I suppose probably better, is that at the 4th year of our undergrad program, students can choose elective courses which are shared with grad students, so grad courses. And so at that stage, they can have a flavor, a sense of what it is to be an actual researcher or in general a professional working on quantum technologies with more specific details. But first and foremost, I guess, as an undergrad, I think they should learn all the basics, right? To have all the core courses. And then when it comes to the 4th year, introducing a number of courses which are part of the grad program, I think is helping us a lot without necessarily developing a specific undergrad program only tailored to, quantum technologies. So at least that's the way we are at this point in time developing these programs in Waterloo.
Can I just add something very short to that? I think image is everything, and I think it's great to make quantum something very aspirational for the very best students. And so something we've done is set up a program, an undergraduate program, which has much higher entry grades. So it's much harder to get into than standard physics. And it's called a research placement program. So students spend every summer, when they're not in the lecture hall, in one of our research labs and helping out with research. And I think that's a good way to make quantum more prestigious.
And perhaps if I can further amplify what Jacob just said, actually I forgot to mention, we have something similar, but it's something which is not specific to quantum in Waterloo. We have a co-op program, so the students every year, they must spend a term in a research facility, in a lab, either locally or not. So we do have something similar, but it was not triggered by quantum necessarily, but it's definitely applicable also to the quantum world.
Do you want to add something?
Would you like, no?
Please.
Maybe I'm just going to add that there is something quite similar, I think, at KFUPM, concentration program that is already embedded in the undergraduate program. I think this is very well suited for quantum computing, especially that's very niche. I think undergraduate program only dedicated to quantum computing is going to be a little bit difficult. So I think the CX program that KFUPM is currently implementing is the best approach, in my opinion.
Can you tell us more about the career opportunities your students, whether through your startups or through other avenues, have had going through a quantum technology program?
Yeah, sure. Once again, I guess providing a few examples from my own experience, I think is probably the best way to answer your question. And so among my students, just to give an example, I think one of them only ended up becoming an academic, so in an academic position, so he's a professor in University of Boulder in Colorado. The other students, one of them, for example, now is a senior engineer at IBM at Yorktown. Another one is a co-director of a startup company in Sherbrooke in Canada. And another one works at Xanadu, for example, as a theorist. And so, furthermore, a few of my students started their own company, actually. So while still pursuing their studies under my supervision. So at least in Waterloo, there is this nice policy where the university does not own IPs, and so you can, these definitely help people, creating their own companies already at the early stages before even completing their studies. And so, yeah, 3 of my students actually who founded the company are here. And they will give a workshop this afternoon. So I think that hopefully answers a little bit your question.
Professor Jacob, you earlier mentioned about the reach of your specific masters, of the global masters. Can you tell us how how like this kind of global collaboration can impact the field of quantum and can help foster the development of workforce, whether here locally in Saudi or globally across the world?
Yeah, so I mean, the first thing is international collaboration is fantastic and it's crucial and it should be top of the agenda. And workshops like this are a really good start. I mean, people have come from all over the world, from all different stakeholder groups. I've had some amazing conversations myself, and collaborations start to form exactly at events like this. I think that the national program that has been set up in Saudi Arabia should be very outward-looking. I'm sure it will be. It should have an international perspective with a steering board with international members on it. And funding, of course, is always crucial to lubricating the cogs of research. And I know that can be difficult funding projects that involve international partners, but something that can work well and has been done in the UK is for funding agencies to come up with agreements with other countries, bilateral or even larger agreements. So the UK has recently run a joint quantum program with Canada and another one with Japan, and they've been incredibly successful, so I would advocate for that. And another direction, I think, is to use international companies as the conduit, if you like, for international partnerships. So if you give some funding to a company, they put in more money, they bring along all their international partners and collaborators, then you've got a ready-made international collaboration. I think that's a really good way of everyone contributing to a common goal.
As a last question, I don't know if, I mean, Professor Jacob already answered the question in ways about what kind of lessons from international initiatives in developing a quantum workforce you think Saudi should take in.
So I would strongly encourage here this university, this institution to definitely start their own. I would say, personally, I would go for a grad program strongly involved in quantum technologies over an undergrad program for the very reasons I explained earlier. And you can start, for example, with a master program, before a PhD program, just to get started. That's, I think, is a good, sensible way to get started. So if you look at all the international programs which people have developed worldwide, I guess that seems like a good starting point. So I would go for a strong grad program. Perhaps again with some connections to the last years, you want to motivate undergrad students to actually eventually start this grad program. And so to do that, you can throw in a few courses which are shared between the grad program and the undergrad program as elective courses towards the end of their bachelor degree. And I think that for us is helping a lot to retain students and to sort of motivate them to start our program, our grad program on quantum computing.
Maybe my input, like if we're going to talk about it locally, I think we need to increase the influence of quantum computing, or like the programs, courses, etc. in quantum computing a bit more in our universities, like in Saudi. I know KFUPM is doing a great work, but I think KFUPM is like 1 out of 35 Saudi universities, if I'm not mistaken. I think we have a total of 35 universities, which is a considerable number. That I think at least 5 of them should, one or another, have a quantum computing program, at least like a CX, even if not a graduate program, but at least a CX, like a concentration.
I think I've already answered this largely, but can I add one more thing? And that is, I agree with what everyone's saying about a graduate program. I think that would be the key thing to focus on. But I would encourage you to add broader skills training as part of that. So not just the physics and the research project, but adding in some skills training in things like business and entrepreneurship and public policy, because a lot of your graduates will go into those roles, and it's a very, very powerful combination to have the technical skills of quantum technologies along with those other skills, those business-based skills, those public policy type skills. I mean, as Matteo said, only one of his students has become an academic. Most of these graduates will go off to be the future leaders of the quantum tech industry. So having those broader skills would be really valuable to them and to Saudi Arabia.
Thank you so much for our panels. This is the end of our panel. We'll be having a panel right now with led by Professor Flimpman on infrastructure and supply chain Okay, thank you so much.
Okay, thank you, Abdul Malik. So I would like to invite Professor Irfan, Dr. Hammam, Dr. Mark to the stage. Meanwhile, I think this is almost 4 p.m. So the first work, please, onto the stage. Just to announce that the workshop by Red Blue Quantum is starting now. This is going to be in second floor in the atrium. Okay, so we're going to switch gears a little bit from workforce development into value chain and supply chain. So supply chain we know because this is part of building infrastructure. But value chain, that includes industry collaboration and funding and so on. Luckily, we have Dr. Muhammad Al-Sharif from RDIA, who's going to talk tomorrow more about the funding opportunities from RDIA and so on. So we're going to shift that toward probably tomorrow. But today, I want to get the opinion of our esteemed panelists about things or challenges of how on building the infrastructure when it comes to quantum computing and technology. And I will start with Professor Irfan. I know that you are running, mashallah, one of the largest groups in quantum computing. Aside from politics, international politics, what are the biggest challenges when it comes to quantum supply chain today? For example, in a university just like us starting to build our own facilities, again, when it comes to sourcing materials, manufacturing, integration of equipments and so on. So what are these foreseeable bottlenecks in terms of the supply chain and how to address them?
Thank you for raising the question. I will focus a little bit on superconducting technologies first, but having now been running our DOE center for some years, I can comment on, of course, ion trap and atomic elements, and of course, I would imagine you have things to add to that. I think quantum computing is transitioning from something which is bespoke to something where you can buy components. So there are two pieces to that transformation. In the beginning, of course, it was difficult in our field to just have components that would work in those particular extreme conditions. So in the level of cryogenic components, it was simply try it, maybe it works, and then you make a list and you share that list with people. So that's not a very stable way of doing this. Moreover, processes change, companies change. You would have some manufacturing process which has become different and no longer compatible with what you're doing. So the second element then, of course, is benchmarking and testing. And I remember very vividly, we were a part of a DARPA program once that said, you need to really verify your results. So we had 8 dilution refrigerators running. We took the same qubit and put it in 8 fridges, and all of them had different answers, right? Because the filters were slightly different and so on and so forth. So coming up with the right set of standards for what is a quantum technology, agreeing upon that as a community, and this is also in David Key's talk about reproducibility, that also goes a long way. And in terms of, for example, things that are in other domains, still getting control electronics for things that run, for example, in the ion domain or atomic domain, in a way that's scalable, has the right phase noise, et cetera, the lasers that are stable from various vendors, getting other vendors to actually make that product for you, getting enough of a market share for doing that. Those are things, at least from my point of view.
Thank you, Professor Irfan. I will stay with you because I was, again, just want to double down on the infrastructure. So again, KFUPM we are trying to build our own infrastructure in terms of superconducting qubits and cryogenic and so on. So from your experience, what kind of investments should such universities like KFUPM should do to support such large scale or getting into conducting high-level research, especially in superconducting devices, but not only that, into photonics and so on. And how can we make this collaboration with the industry to support such investment?
So I'll address the superconducting piece. I guess other folks can talk about photonics or other aspects. There's one element, which is what infrastructure do you need on the ground in the university? And then the second part of the question was how can industry or companies sort of come into that particular mix? So I think topics of science and physics sort of rotate fast through what's popular and what's not, right? And universities don't do that. We teach for basic skills. We go ahead and then, of course, have application to those skills, as the previous panel talked about. So having the background infrastructure is important. Having machine shops and electronic shops and people that learn about the basic skills and don't do turnkey science. Certainly at some level this becomes an engineering endeavor, but at the level of universities, we don't do catalog physics all the time. We're trying to push that envelope. So making sure that we simply don't have something that requires a short-term investment, but something that has a background investment in the requisite skills is useful. And that's a natural partnership with companies that want to provide you that equipment, that want to have their equipment tested and the like.
Thank you again. Dr. Mark, I know in Quantinuum you're building ion trap-based machines, and those machines are not particularly easy to build and operate. I mean, this is the same also for other quantum computing machines or hardware. So one model that we are seeing being adopted by many companies is providing this as on the cloud, right? So this is cloud-based services, whether it's hardware or software. I'm not sure about the hardware, but this is something we can think about. So what is your take on such cloud-based quantum services, and how can that support research groups into doing such research in different quantum technologies?
This is on now? Good. So thank you, Professor Philemon. That is correct. The vast majority of our clients at Quantinuum that access our machine, it's via the cloud. So JP Morgan Chase, for example, is one of our biggest customers, and they buy a huge amount of time on it. You can also access it through Microsoft Azure or through Oak Ridge National Labs. But there's many reasons why a research group would not want to do that. So given where we are, so one idea is that a lot of countries have laws about data privacy. They want all the data to remain in the country for whatever reason. Another reason just might be like a pharmaceutical company or a defense company or something. They might also want to have their quantum computer on-prem. And so the good news is that we are starting to do this. It's actually a very timely question because just a few days ago, we completed the installation of a quantum computer in the RIKEN facilities in Japan. But it took us 2 years to do that. And so kind of circling back to your previous question about supply chain, yes, it took us a long time to design and install that quantum computer. That obviously has to be improved quite a bit. Our longer range plan is actually being able to fabricate this and print it on a chip, and we're already starting to work with companies on that. So I imagine towards the future we'll have both on-prem and cloud access options for people.
Now, did any of the export controls hardened or kind of limited this installation of the quantum hardware in Japan?
I know that that's a good question. I should preface this, I wasn't on the team that negotiated it, so I don't know the details, but I know that it took, I think it was like 1.5 years of negotiations, and that's with Japan. The US and Japan have a very good relationship, and so I imagine for other countries, right now it might be worse. I am hopeful that as quantum matures, countries do seem to be realizing that this is important, and that international collaborations will need to be made. And so I'm very hopeful that at high-level political levels, there's kind of an improved process for facilitating this.
Thank you. So moving on to industry collaboration, I want to ask Dr. Hammam, having working in the industry for a few years, so how can we start this kind of partnership? And this is an everlasting question, right? So how can we start this partnership between the public-private sector first, and also between companies and universities in order to facilitate not only the research, conducting research in both parties, but also facilitating the supply chain between moving from the industry to universities and vice versa in terms of the IP. So how do you see this partnership between the companies and universities from your point of view?
Well, I think from, particularly for Saudi Arabia, I think the government has to play a role, so the government has to facilitate this kind of partnership between private sector and universities. just to kind of get the ball rolling. And I think once the involved parties start to see the payoff from this kind of collaboration, once we have a few successful startups and we make big news, then the market by itself will kind of take over from there. So I guess what I'm saying is we need a kind of a first spark, some few successful examples, and I think these can be targeted investments or partnerships between parties in the private sector and universities that are catalyzed by the government or encouraged by the government that can serve as success stories to encourage more of those.
Okay.
I just want to make one more point about your question for export control. So I work for Keysight, as you noted, and we have, we basically sell control electronics that are used for controlling, superconducting qubits, among other technologies. And we've in the past faced problems with export restrictions. Our customers have definitely felt, the bite of these regulations. And, well, we said we're not going to talk politics, but I think it's reasonable to expect that in the future, such restrictions are not going to ease. They're not going to get easier. They're going to get tighter and tighter. Hopefully not, but they might. And that's a real risk. And so I think one kind of important strategy to mitigate that is to diversify your supply chain, kind of try to, as much as possible, to have backup plans, and as much as possible to kind of bring, build your own technology whenever you can, essentially, so that you're more resilient to big disruptions.
And when you say build your own technology, do you talk about the hardware or the software?
Well, I'm thinking hardware, but it applies to software as well. It doesn't have to be the whole thing. It's just you can identify critical components that are that are kind of critical for your operation or critical for the the operation of the institution you're thinking about, and you've got to make sure that you've got multiple plans for securing these in the long term. Manufacturing them yourselves is not a bad idea. Right.
Okay. Great answer. So to conclude this discussion, I would like to have a concluding remark from each of you, talking about the opportunities and also the challenges when it comes to building infrastructure in Saudi universities or universities in the region, and how to, if there are some risks, how can we go around such risks?
So I think going back a little bit to the point that you just made, how does one nucleate meaningful interactions? Just thinking back, one of the things that we worked on very early was the dry dilution fridge, one of the instruments that you're getting at the moment. For us, that started in 2005 when I first joined Berkeley. And it was motivated by because I thought I couldn't buy liquid helium. Quantum computing hadn't taken off, so there was no money in the field. So one's helium budget was at least 50,000, 100,000 a year. So I said, wouldn't it be great if we never had to pour liquid helium? So I found a vendor at the APS meeting who was making dry pulse tube coolers for microscopes. And that started a collaboration with the Walter Meissner Institute in Germany. And that's how the first commercialized dry fridge was made, which we still have, and Andreas Wallraff has in ETH. That company was bought out by Oxford, and they continued to make fridges, so on and so forth. But it was truly something that was a need, right? It was a need, and you had engineers coming in from different aspects. And I remember going to Germany, we would argue over which part should be gold-plated or not so we can still make money on the fridge. But again, those are things that are in grassroots level and nucleated there. And I think similar things are needed in the university setting. What is the problem you want to solve? Right? If it comes from top down, it's a little bit difficult to implement. It's difficult to get people motivated. But once you start building on a core, which I think is solid, then I think sky's the limit.
We don't need a dilution fridge. No, one of the advantages of ion trap technology is that keeping it cold helps, but it's not absolutely essential like in other technologies. And as I mentioned, our 5-year plan is to be able to fabricate it on a chip that would work at room temperature. There are many opportunities about doing quantum computing here in the kingdom. At Quantinuum, we're very focused on practical use cases. And our technology right now is, we're about 2 years ahead of where we thought we would be. We published a roadmap several years ago, and we're actually several years ahead. And in a few months, we'll be publishing our, releasing our updated architecture, which will be about 1 trillion times more powerful than what we have today. And so we're already starting to look about commercially viable things. And of course, as many of you know, chemistry, which would feed into petroleum and refinement and such, is obviously one of the big commercial opportunities. And so, so we're very excited about working with you here in the kingdom.
Sorry, what was the question again? Okay, yeah, I can say a little bit about that. So, okay, so let's go back to superconducting qubits, control systems, control solutions, control electronics for superconducting qubits. I think there is a kind of, the way this is heading is that these components are going to get more and more miniaturized. They're going to get more and more high tech. They're going to get integrated with, things that are viewed as being, highly advantageous for a country to have. And so they're going to get more and more export controls. And so, this has to, so I guess, there should be a national strategy for securing these components in the long term, because, it is really anyone's guess what's going to happen. And once, it is very reasonable to think that these components will play a critical role in a future quantum technology. Like, once we have a scalable superconducting quantum device, it is most likely going to involve some very highly specialized chips, semiconducting chips, and control electronics, and those will be highly prized. And so planning ahead for that will be a kind of a smart move.
So much for the esteemed panelists for the insightful discussion, and I hope we had few takeaway messages so we can build our strategy upon that. So before I conclude, I would like also to thank the audience for sticking around. I know it's a little bit late, 4:30, but thank you so much. This was a very exciting day. We heard interesting talks, very insightful talks from Professor Irfan and Dr. Hammam. So we are concluding today's agenda, but we also have another exciting full day agenda tomorrow. We're going to hear talks from, we're going to hear from Dr. Mark, as well as Professor Jacob and Professor Matteo, and many others from different industries. So again, I would like to thank the esteemed panelists. Thank you, and looking forward to see you tomorrow.